As usual, just waiting for Twitch to catch up. There we go. I should be live. Welcome back, everyone. Unplanned stream this evening. I usually don't have free time on Monday evenings, but today I do. So I decided to make a short stream and make some progress. So, last we left off, we are in the middle of a refactoring of the analysis phase. We are splitting it into two sub-phases, a renaming phase, or name resolving phase, during which we figure out what each name means in each context, and a type checking phase in which we check that everything is consistent. We used to do both at the same time, but splitting them gives us a lot more flexibility and guarantees that we can output something that is a lot easier to use downstream. We are in the middle of the refactor, nothing compiles, so let's just jump right back in. We were in the middle of this validation stuff. Last time, we made some progress on validating an expression that appears in a constant by mostly copying what we had before the refactor and removing what is already done in the name resolving phase and keeping only what needs to be done in the type checking phase. But we ran into something that I have not implemented for this part of the thing yet, which is, we have a definition that depends on another. For instance, a constant a that depends on the constant b. It's not as simple as just, we just fork over to validating constant b then, because we must detect cycles. Because if a is written in terms of b and b is written in terms of a, then we would have an infinite recursion. So we're going to need to be a bit smarter about this. So I think I want to start with this because that's something that's going to be useful. And it also means changing slightly this top level validate function that takes a definition and, validates it, type checks it, and everything. So here, what we do currently for a constant, we check whether it has already been validated, because sometimes if we have a constant a and we have both b and c that depend on a, we might validate a and then we validate b that calls a validator of a, and then c that calls a validator of a as well. We don't want to validate a 3 times. So we already have a cache of has this thing already been validated? And afterwards, we always insert the name so that even if everything fails, validating the constant fails, we will still label it as validated, which means future attempts will not try to validate it again. It's always in the cache, regardless of whether the validation was a success or not. And then we actually call the validation stuff. In the case of a constant, validating the type, validating the expression, checking that the type of the expression matches the type of the declaration, and then inserting it in our values. This is already incorrect. We're going to have to fix it. The thing is, this structure is going to be the same for basically all declarations. So what I will want to change is remove, change this a tiny bit and extract some of this logic of avoiding circular declarations and inserting things into the cache and catching errors so that if a top level declaration errors, we still try to do all of them. I'm going to make that a function and use that in my top level validation functions. So let's do just that. We will want to have something like a validate definition with, or maybe just validate definition function that given some monad m, we will need more constraints than that, but for now that's good enough. And given a unique, what do we use currently? We use name. Okay. Given a identifying name, and given some kind of action in our validation monad, I'm hesitating, should it be A or should it be unit? I think it should be unit in the sense of we want to guarantee that this should not return a value. Everything should be put in the cache, but not return an actual value. given an action in our analysis monad. Oh, is it called analyze? It's called validate. Analyze is the old name. Yeah, it is correct in a few places, but not in all of them. Let me fix that. And I will probably want to rename them as validate T since they are technically transformers, but that will be done later. Okay, so for now, again, none of this compiles. We're in the middle of the refactor. So validating a definition will take the action that actually does the validation and return a corresponding action wrapped with all the stuff that we need. So we have the name and we have the action, or the callback if you want. What we're gonna want to do is, first, I'm gonna go back to the monad. We are going to want to keep track of the definition stack, so that if we end up with like, oh, we looped A depends on B that depends on C that depends on A, we want to be able to put that in the error message. So we are gonna want to keep track in our state of dependencies. That's not a great def stack. Def stack is not a great. It happens to be a stack, but that's not. Well, I guess. Dependencies is probably the best name, even though it's going to be a list and not some kind of mapping of dependencies. No, I think since dependencies the type will just be a list of name, I think call stack basically is probably, or definition stack. Definition stack is probably the best name. There we go. Okay. So what will we need? First, we will need to check, are we in a cycle? And we can look back at the old code, which I think is in core, the top of the file somewhere here, where we had something equivalent. Where was that? Analyze definition. There we go. View info stack. There we go. And that's what I'm looking for. It's going to be different, of course, in our case because we've changed a few things, but that's the root of what I want. I want to get the validation. We call that the definition stack, I think. A second ago, the definition stack. I want to inspect the definition stack in my state. Oh, but making it a list, the problem is then I make searching for a particular element a linear thing, which I don't want, because big files then become kind of unwieldy. So I probably want some kind of set, but then I lose. Then I lose the dependency kind of thing. Could I make that instead a hash map from current name to previous name? So like A depends on B, A depends on C, that kind of stuff. Well, not. Would that solve the problem of being able? It would solve the problem of being able to quickly check whether we are in a cycle. It would not solve the problem of giving us a way to include in the error message the actual cycle that is the problem. Hmm. Because at this point we are already in the new context. That's complicated. I guess a solution would be an ordered a insertion order set. So a set that has the property of being easy to look into, but that maintains the insertion order. There is one in Haskell. Haskell set. I can't type, I'm afraid. Insertion order. Uh, ordered set somewhere. Data set ordered. I think that's the one. That's a candidate. That might be not what I want, but I can look up ordered containers on Hackage. There we go. That's in 0.2.4. But I think that's the one I've used in the past. And the ordered set behaves like a set with the same asymptotics, but also remembers the order that the values were inserted. So that means we can always, if we need for errors. Is that the one I've used? I do not recognize those operators. Is there more than one, actually? Have I used another one in the past? So I'm assuming then this is a to list kind of thing. This is an is list. Okay, yeah, to list. That's the thing. Is there another one, actually? There's an OSTET package. No, it must have been the one, but maybe it has been maintained since the last time I've used it, and some of those operators are new things that I do not remember. Okay. Let's use that. So that's ordered containers. I don't think I have it in my dependencies just yet, so let's add it. Dependencies. I don't have it. Ordered containers. Here in the monad, rather than a list of name, let's make that. So otherwise, I just could go from the validate context, I suppose. Let's use an OSET, and actually, I will want this to be a base name, not a name. And for the value cache, the only kind of values we will have at the top level will be constants, and constants are no longer expressions, they are const expression. Okay. So I just need it is data set ordered, and I just need the OSET for this file. Okay. Now, what else do we need? I think that's about it. So now, rather than using this member in the set kind of thing, we are gonna need to import data ordered set qualified as OSET. And we're gonna need to use whatever is the equivalent, which is probably just gonna be member as well. Member, perfect. And how do we insert something? There's this whole bias thing that I'm not familiar with. Indexing. Insertion. I suspect this is just about like in which order should I insert the things. Oh, Hello, everyone. Yeah, I'm writing a compiler in Haskell. And yeah, I think here, since I will want, if I ever need the list of the dependencies, I will probably want it in the order in which they appear, as in A depend like cause A call to B that calls to C that calls the call to A. So I think I will use one of those two. Wait, the pipe appears on the side whose indices take precedence. So I need to use this one in all likelihood. Or this one. Okay, so I will want to... And actually, I don't... I can just qualify... No, as offset, I think is correct. So... I look up the name, which is, again, a base name of the definition that we're currently doing in the definition stack. If we have a cycle, then we report an error, which is cyclic definition root name, and this will probably... We might want to get the definition stack, actually. So that would be... Let's get the def stack by just getting use vs definition stack. And then def cycle is no longer required. This is if... And I can write it in infix so that it reads better. If the name is a member of the def stack, then report an error of a cyclic definition of the root name and the def stack, I suppose. This will not compile yet, but again, nothing compiles at this point. We'll fix that. And otherwise, we can be on our merry way. The first thing we need to do is modify the definition stack to actually insert this thing, to be able to, like, before we process anything, to be able to detect that if we end up depending on itself. So we are going to need to modify the VS definition stack in our shared state by applying a function on it, and this function will be this operator. Let's do this one. And we are inserting the root name. It is just name. We are inserting the name in the set. And again, it's an ordered set, so the order will be kept. So I guess here I could do an offset to list here. If I wanted to be extra, I would actually filter this to only keep... to drop everything before the first instance of name. Maybe I should do that. Which one is it again? Data list Haskell. Is it break that I want? I think it is. But let's check. Come on, Hackage. Well, if Hackage doesn't load, it did. Break, where's break? There we go. Given a predicate and a list, gives me two lists, and gives me the longest element that does not satisfy P. Okay. So basically, if I do a break on equals the name of the thing I'm currently doing, I'll get the first list, which is everything that's before, and then the list that is everything that starts at that thing, which is what I want. So I will want to do something like list break equal name. And I will get two lists out of this, and I want the second. And I just need to have L in scope, which I don't, which is data.list qualified as L. There we go. So we're back here. Actually, I'm going to put this function above this one. Oops, sorry for that. Now, we have checked that we are not in a cyclic definition, that this, like the thing we're trying to define, to validate actually now, it does not depend on something like on itself, basically, recursively. So first we can do is put it on the stack, but we will need to guarantee at the end that the last thing that we need to do, this will be a bracket kind of thing, where at the end, okay, let me just finish this and I'll answer your question. We'll need to make sure at the end that we remove. Actually, does this set have a way to remove things? I think I've seen the delete. Yeah, delete. Perfect. Perfect. So I will want to modify that thing by doing a offset delete of the name. So that's, and we will need to guarantee that this always returns. So we're going to need an equivalent of finally here. So the language I'm trying to pass here is a made-up language based on Rust that looks a bit like Rust. It's supposed, except with the parser I have chosen, I have one element of syntax that's different, but otherwise it's supposed to be basically the same syntax. So like syntax highlighters and formatters work the same. Do I have a file open? I don't. Like, you know, basic functions like this with template, with like type arguments, and you can and structures and all of that stuff. Like it looks like Rust. That's the point. What we compile to, however, is not a normal binary, a normal image that you can run. We're compiling to an esoteric language. Specifically, we're compiling to Piètre. And Piètre is a esoteric language in which a source code is an image. To give you an idea, if I that and I look at this image, for instance, and I zoom it up a bit because this is way too small. This viewer doesn't. Oh, maybe first is the resized version. It is the resized version. There we go. This is a valid Piètre program. It does almost nothing. It prints 2 characters and then it exits. But the goal is to translate Rust-like stuff into that. And while this is not a serious project in the sense that like no one uses Piètre seriously as a language, I am trying to keep the compiler itself as close to a real compiler as possible. So all of the faces, all of the different things. The reason there is like some syntax limitations is I'm using the same parser that GHC, the Haskell compiler, uses. I'm using Alex and Happy. At some point I will replace Happy with megaparsec, but for now I'm using Alex and Happy. Our lowering into IR, the IR we are using is based on the LLVM IR, and at some point I'll probably do a converter from our IR to the LLVM IR as well. Like I'm trying to keep this compiler as close to a real one, like to make it a real one, despite the fact that our goal is, again, making images. The last part, so the backend is done. If we have some bytecode, as I've called it, which is like series of basic instructions, generating an image we can do. That image was generated by the backend of the compiler. Some of the front end is already done. We have parsing, we have the old version of the analysis phase, and we have some of the lowering into AR. What we're missing is the code generation from the IR, generating the bytecode kind of thing that is able to like be translated into an image. And I'm rewriting the analysis at the moment because I didn't like the way it was written in the first pass. That's the project. And so now I am again rewriting. It's a fun project. It's been going on for a few months now. I started, I think, February or March, but I haven't been super regular about it. And yeah. So we will need to do some checking here, as in a sense of like, this needs to be kind of a finally. It needs always run. Otherwise, we could have an issue where dependencies are not tracked correctly. However, the only kind of error tracking we will do will be explicitly with our own error tracking mechanism, so we will just have to use something like catch all, basically, since anyway, each definition will be processed independently. So, with that, we have solved the problem of like definitions might be recursive. So if we end up here and we end up calling the action, we guarantee that Actually, I think I'm gonna make it an A here so that I can do the try and always kind of thing. Or maybe no, actually. No, I'll keep it a unit, I think. I think I will want the things to be given here to always be unit. Okay, so here we put the thing in the stack, we perform the action, and then we pop the stack. So if action ends up recursively calling over the definition, it will add stuff on the stack, pop it back, and so on. I don't have the diagnostics monad yet because again refactor, but we know that we will have like a try function and so on. And basically what I will want is a void try. Try makes it a maybe value and catches potential errors even if the overall result will fail, and void makes it like this gives me a maybe thing, I don't care about it. I think I will at some point introduce an alias for always being void try. So always action. And because that's not the only thing, we also only want to do this action if we have not defined that thing yet. We probably want to do the check first. There's no point in putting stuff on the stack and modifying the stack if we have never encountered this thing before. So I think this check here is probably should probably be first. We have in our monad here a validated thing, which is just a hash set of the things we have validated, which should probably be a base name here, not a name. Since what we care about, should it be a name actually? No, I think it shouldn't. The distinction is a base name is like names are things that uniquely identify something within the context. Yeah, I do allow. I don't think I allowed recursive type aliases because since there's no type families, there's no branching, so there would be no way for it to. There would be no way for it to terminate, basically. So having a type alias A that like depends on the type alias B that depends on the type alias C, perfectly fine. But a type alias A that depends on B that depends on A would not terminate, so no, I don't allow it. So name and base names are things that like uniquely identify something within the context of a program, like a unique symbol, for instance. At the end, when we do the linking, we use names to link things. And the difference between name and base name is that the name includes type parameters. For generic functions, for instance, I do kind of a C++-like thing in my implementation, where I will have a distinct symbol name for each instantiation of the function. So if I have a function foo that takes a type parameter, and I have part of the code that uses foo of int and a part of the code that uses foo of boolean, then at the end I'll have two distinct symbols, foo of int, foo of boolean, that will be like compiled, two different functions compiled differently, basically. And the name, therefore, would be foo plus the argument, so foo plus int or foo plus boolean, that makes a unique name, and the base name is just a foo part. For definitions, here when we are going through a file and we're trying to look at all the things and validate and compile the list of symbols and types and everything, the thing we care about is have we already processed that definition, regardless of which symbols it ends up creating. So I think this should be a set of base names, not of names. So here that means I'm going to copy this, which is wrong because it's copied from the pre-refactor, but it's close enough. So an unless m takes monadic action in our current monad and returns which returns a boolean value and performs the action only if this did not return true. And what I will want to check is it's going to be a hash set. Why do I have set here, actually? Do I have actual real sets? I don't think so. Probably copied from the old code. Anyway, so we will check in the set of things that we have at least attempted to validate is the name part of the set? If that's not the case, then we need to do all of this. Otherwise, we don't need to do anything. And the very thing we're going to do is put the name in the set, because again, even if all of this fails, well, not the cyclic definition, I suppose, the cyclic definition stuff, I suppose, but if like we try to validate a type alias, and it's wrong because it points to a type that doesn't exist. But then we have a second type alias that points to the first. We don't want to recursively try to analyze the first one again. So here, we always modify validated. Is it insert for? I think it's just insert to put the name inside the set. Wait, no, can't do that. Because if I do that, then the cyclic definition will never trigger. Because I'll try to analyze the thing, and I'll... The thing is that I don't have this kind of option for the types with the pipes that you describe. So since there is no branching, it would not be able to... It would not be able to... yeah, this would not terminate, I think. I'm not able to express something like this in this made-up language. Because again, like this requires branching. Like there's options here. And here I wouldn't... like, I can't do that. It's not a bad idea for an extension to the language, but we're not there yet. Let me just think about this for a second. The problem with this idea of putting this in the set is... Oh, thank you. Again, you don't have to do that. I'm very glad that you're enjoying the project. So the other problem is, if I label the thing as validated regardless of whether it succeeded or not, it means that this cyclic definition stuff will not kick in, which is a problem. So I guess we can't do that. We need to always do that at the end, so that the cyclic definition stuff kicks in, and at the very end, we put it in the list of things that have been validated. Yeah, okay, I think that this is now correct. With that done, we have deduplicated the analysis by using the validated hash set. We have done the detection of cyclic definitions to prevent that, and we throw an error if that ever happens. And I think that's basically about it. The only thing is like here, we always perform the action, because since we don't return a value, we insert something in a cache. Each action will decide what it does. So this will be validate here. Given the definition, we'll do for each of them. Actually, no. The others are going to call validate definition, I think. So here, this is just going to be validate const. This is going to be validate function. I'm going to move this check into validate function, I think. Oh, no, actually, this check probably needs to be here. Because, again, I deal with generic functions the same way as C++ does, kinda. As in, if a function is a parametric function that has a type parameter, I don't actually do the type checking until it is instantiated, and then I create a new symbol for the instantiated version, and I type check that one. So I only perform function type checking if a function is not generic. If it is, we don't do the type checking. We don't put it in the cache. Its definition remains available for other functions, and it might be processed at a later stage when instantiated. Okay. So I think this remains this way. Is there an unless? And let me check. If I open a GHCI, I know that when is in there. Is there an unless? There is indeed. So rather than when not, I can do an unless is generic info. There we go. Now, we can rewrite validate const as being... do we have the base name anywhere? Because this function assumes that the base name is in scope. I don't see it. So let's go back to look at the AST. What is in a const info? AST passed. We have also changed all of that. Let's see. Oh, it's probably in common actually. Const info. The const name is the identifier. Okay. Oh, but here I have validate with a name. I don't think that's correct. I don't think we have... Oh, no, actually, it might be correct. Well, this might be a base name, actually. In the sense that since now this is not the analysis phase, it is the second half of the analysis phase, the previous sub-phase, as part of the analysis, is the resolution one, where we do all name resolving so that we don't have to keep the scope for generic functions. Its output will be, if I resolve a thing, I will get at the end, given a base name and a definition passed, I get the definition resolved. So I will probably get a hash map from base name to definition resolved, which, if I remember correctly in our monad, is, there we go, the definitions that are in scope from base name to definition resolved. So it makes sense that when we do validation, we are iterating over a container of both. So we do have the base name and the definition. I am going to just forward the base name to this function. So the validate const function will take the base name. As a result, since I know the base name and the base name is the only key, I was thinking of like letting each function, validate const, validate struct, validate enum, and so on, call this validate definition and decide what its own base name is. But since the base name is known at this top level, there's probably no need to do that. So here, I can probably instead do a validate definition, which is this thing. And perhaps I can, in fact, inline it entirely. I don't have... to use a separate function. This is what it means to validate a definition. So unless we have already validated it, it's already part of the cache. We check for cyclic dependencies. Here, we call always of an action, and that action, this always thing that we want to always succeed, well, always return even if it didn't succeed, will be always, it's this thing, always with some context and the location. Definition of the capital T is wrong, this is a lowercase thing. And the action we perform here depends on the type of definition that we have. I might put it here. There we go. And those paths are temporary. I'm actually going to replace them unimplemented, which is a lot more explicit. There we go. And validate const, unless is generic validate function. There we go. Okay. Now, here we have the base name, the const info. The actual name will be base name plus no arguments, because there are no type arguments to a constant. This unless goes away, this validated goes away, and now this is what it means to validate a constant. We validate the type, we validate the const expression. This means, since I'm not doing, trying to do any try here, it means that if we fail to validate the type, then I will not attempt to validate the expression. Maybe I shouldn't do that. Maybe I should do a try here, a try here. That way I collect errors on both. Which I'm actually going to rename as attempted. And then validated type becomes ensure of the attempted type. And validated expression becomes ensure of the attempted expression. That way, again, if one of those, like if type gives me an error, I guess I don't have to do it. I don't have to do the try here. I could just do the validate and not do, yeah, I might do that. This is directly, it feels better to have it symmetric, even though it's a tiny bit less good. And so if this execute, it means neither has written any error. And now we can do the last check. If the type is the same as the type of the expression, then we're fine. Otherwise, we report an error. And base name, oh yeah, of course. I don't need to give the name as an argument, because the name will be part of the context. So I can always get it with current name. That's good. We're back to this now. And here at the end, I get the base name. Wait, so this const name has to come here now. Do I still have current name? Is that still a thing? I do have it. Okay, but that is a name, not a base name. Is that correct? Nope, the context is a base name. So current name should be a base name as well. So I get the current name, the current base name. I create the const name. And the last thing I do is I modify the result. Yeah, this validate thing is looks like it's able to validate a thing in isolation, but that's not completely true. It depends on the state anyway. So it's fine, I think, for our validate things, just insert the correct stuff in the cache at the end. We insert a thing that maps the const name to a typed expression whose type is the validated type, and the expression is the validated expression. Is that correct, actually? No, it's not. The validated expression is already by itself typed, so I can just use that. I have just checked that they are the same. Okay, so that's validating a constant. Let's have a look at validate function that we can probably simplify quite a lot given what we have done. I'm gonna move it to the top as well. I will split this file into several subfiles, but for now, since I'm in the middle of the refactor and like nothing works, for now have all of those functions in the same file. So this will be a lot simpler because we don't need the location. Type parameters, that's correct. The func name is no longer something that's required at this stage. The unless here, the validated, all of this goes away because it is now performed at the top level. And now this becomes, maybe I want to try to find a way to do this kind of try. Can I do something? Because I suppose I could use tuples and do like an ensure of a lift of a tuple constructor into a thing. Well, no, that wouldn't work necessarily. I think this is okay, even though it's a bit verbose. So that means here we're gonna do the same thing. This is gonna go away. We're gonna do validating the function type, validating a block, which is the function body, and at the end create. Is that correct, function info? It might not be correct since we have changed everything again. Our output for this will be a symbol, which is a function, which is a new thing, which is not there. It is in, if I go back here and if I look at validated, a function will be something in there. Where are you? Oh, maybe not. Maybe I don't have a function type. So maybe it will be a function info, just like we had before. And so this might be wrong. What did I intend to do with this? I think function info is fine. So I think for now, function info is what we want. This will be representation. It's going to be the validated form of the AST, I suppose. Okay, I think that's correct. And that means if we go back to, sorry, validation, where are you? There we go. The result will be a function info with the validate type and the validate body. I think that's correct. And the thing we'll need at the end will be using the base name that we get from our current context. There we go. The actual name will be this base name plus type parameters. So again, if we're trying to validate a function foo with an int argument, this will be foo plus int. And we insert that into the symbols. I think. Oh. Yes, of course. Functions are also values. So we insert them into the symbols that need to be compiled, but we also need to insert them into the values that are accessible at the top level because functions can be used in value contexts because we have a half-baked support for function pointers. Function name expression. There we go. Should that be a const expression, in fact? Should that be a const expression? I think so. Because those are known at compile time. So a function name const expression, which will contain the name and the function type. That is to say, if we have a function first at the top level, then there is now, after compiling this, something at the top level. Wait. We probably don't want to do it that way. We probably don't want to do it that way. I don't think I want to insert the value into the cache in this way. Since when I do dependencies across module, I think name resolving is enough. I need the definition, the resolve definition. I don't need this validated version, I think. Or do I? No, I might need the validated version. So if I need the validated version, that means I will need to create... I don't need this. Because since name resolving happens first, the name resolving will have done all the things of looking at the imports, so I will know that if a function does some kind of function pointer thing, I will know to what function it points to. I don't need to add that to the values at the top level, at the constants at the top level. So this is not required. This is not required. Okay. Now, the last thing is I will probably want to do the same thing that I have here, which is I probably want to do... no, actually, here, I was going to say I want to do the try to be able to, like, okay, even if I can't do an analysis of the function type, still try to do the validation of the function body. That way I can collect more errors and show more errors to the user. I don't think I want to do that. And the reason is I cannot validate a function body if I don't know its return type. Because things such as, hey, there's a return statement there, is it valid? Well, I need to know the return type of the function. So I don't think I can do this validate block if the validation of the type did not succeed. And I don't know. I know that my context has a thing for, like, maybe the type... Oh, this will probably be a maybe type of the type of the function. I don't know if this is done as part of validate function type or if it should be done at the top level. Validate function type doesn't exist yet. Perfect. So I think I will here do the thing where the current function type, which is a lens, the current fun type is going to be modified to be this func type. So this must succeed before we can go there. Each thing operates in its own context, so it's fine to modify the context for the scope of the function. Okay. Next. Oh, do I do the loop detection thing as part of the name resolving? Or should I do it as part of the... I'm tempted... There's a thing I was doing before, when the analysis phase was only one phase, which was to do the loop detection. And it was a very basic thing of like, oh, here's a break statement. Are we in a loop? If the answer is no, then report an error, which is like this continue statement or break statement appeared outside of a loop. However, as part of the lowering into IR, we do the control flow analysis. And the control flow analysis performs those checks again. So maybe we don't want to do that check as part of the type checking thing. The name resolving, type checking don't care about whether a break or a continue appears outside of the loop. But when we do the control flow analysis, then we report the error. This means that it removes checks as part of this part of the code and removes internal compiler error from later stages. So I think we don't care about it. And I think the context doesn't have that anymore. Perfect. So we get the function type, we validate it, we put that in the context so that return statements and others can be type checked. We validate a block, which is the function body. At the end, we get the current name. And we create the new function info that contains the resolved type and the resolved body. Okay. we're going to have some of the same issues we had before in the old version of the analysis that I don't know exactly how we're going to fix. The name resolving phase will do things just like, okay, in this context, what does foo mean? Is it a local variable? Is it a function argument? Is it something we have imported from another module? For the type checking, however, I will probably need to have something more than just the cache from base name to definition. I will probably to also have a cache of types, as in this thing that we know comes from somewhere else. What is its actual resolved validated type so that we can do type checking? Which means we're going to also run into the problem of partial function validation. We'll get there. Actually, we might want to do that as part of this. Because I will want basically the type thing to always be... Because a function, validating a function and validating its type are two different things. And I need to validate the type in isolation before I validate the body. And the reason for that is recursive function. If I have a function foo that calls itself, when I am validating the function foo and I encounter a call to itself within the body, I need to be able to reason about, is this call valid in this current scope? And for that, I need the type to be known, even if the body hasn't been validated yet. So I think what I need to do is... I might want to do a thing where when I validate... I might want to do a thing where instead of having this validate function thing that I have here, when I iterate over the definitions in my module, I do a validate function type first that only looks at the type and the type definitions and resolves that, and postpones resolving functions until we have done all of the types first. That way, whenever a function calls another function, we can check the type in our already resolved thing without having to already have gone through all of the functions. I think that's the only way we can do this, because otherwise we run into the thing of trying to go recursively with the functions, and just that becomes a lot more complicated. So that means that we're going to change a few things. I think value is going to change to constant, because we have the symbol cache, we have the type cache, and we have the constant cache. Just to be consistent. Or I remove caches from all of them, and it becomes symbols, types, constants. And I will probably need... since those are the ones I am the result of a validation, I will probably need to have dependencies here, which is going to be for a given known name, what is the type associated with it? We are going to need that from other modules that we depend on to be able to do type checking. I think the definitions will only be used for instantiation of generic functions in this new approach. Okay, I think that's better. Huh, yeah, I was only using a regular set for this, not a hash set, I suppose, because some of this cannot be hashed. That's why I have here this, which I'm going to actually copy here. Qualify as S. Yeah, this is a set of, well, actually, probably as this, and I will want to have. No, I think hash set is already in scope. I think my prelude. Re-export hash set, I think. It does, yeah. So I don't need to qualify hash set, and I can just say S set here. Okay. Okay, so with all of those changes in mind, we can go back to validation. And validating a function will be something we do that's going to be very different from this mechanism. This is going to be validate function type. So I'm going to duplicate briefly this validate function type, which no longer requires the type parameters, I suppose, because this is not the instantiation. So this goes away. So this goes away as well, and this is generic goes away as well. Or does it? No, types are always concrete. So if this is a generic function, it cannot be, its type makes no sense. So I keep the is generic, which means this validate function type is only called for actual concrete functions. Does that make sense? Does that make sense? Because if the goal is to always have the type of the function in scope so that other functions can call it and so on, then that means that generic functions must be in the cache. That's a problem with generic functions then. Okay, let's think about this. I am analyzing the body of a function. I'm an instantiated function. I am calling something foo of int. How do I check that the type is correct? This is a generic function. Therefore, I will need to validate its function type. I guess this is what we're going to do. Whenever I'm going to need, I'm making a call to a function, give me its type. If it's not a generic function, we can just look in the cache. If it is a generic function, we can look in the cache still, but then if it's not in the cache, then we do this validation of the function type with the type arguments. So this is done here like this. And this, therefore, we don't need to keep any of that. The function info will go away as well. And if we look at validated here, we should have a thing that is called a function type. Perfect. Although function type is this, and it is reminiscent of. Oh no, okay. It is what type uses for its function type. That's perfect. So we have to assume that validate function type gives us a function type. That's all good. And that means, aha, that means we probably want to duplicate some of this here. No, I guess we don't, because we will have the retrieval function. Function types are going to be weird. They're not going to be linked to the definitions the same way. We're going to assume that the caller will have made a check in the same way we do for everything else, for every other validation function. Okay? So that means what we do at the end here is that in our state, in our types, so this is constants now. In our types, we insert something that as to the function name associates the function type. Now, that means that when we are validating a function, an actual function, and we are creating the symbol, we have the base name, we have the type. Do we want to add the definition resolved there as well? We probably can add the function info resolved. Because since we will always have access to it whenever we queue something as needed to be instantiated, that avoids having to do more lookups later, basically. The only thing is I don't think this has an ORed instance. So maybe I should instead use like make this a type that has a custom ORed stuff that doesn't care about the function info, but just carries it around to avoid having to do more lookups. That may fail. So this is it just an function instantiation info, and it will contain the name. Well, this is the base name, the arguments or the parameters to be consistent, which is going to be a list of type, and it contains the definition, which is the definition resolved, and actually it's going to be the function info resolved. I will need to do the same thing I have done in this file, which is I'm going to need to distinguish between things with similar name in the input and the output. So this is, for instance, an output function info. This is an output type. This is an output const expression. This, however, is a set of function instantiation info, and that contains a input function info resolved, not an output function info. But it contains an output type. This will not be always necessary, but for a few of them, like function info, it will be, and therefore this will be a lot more explicit. This is going to be deriving show like everything, which is the debug if you're familiar with Rust. This is the Haskell equivalent of debug. And I will want to make an instance of ord for this that is gonna be based on like we'll compare on something that I'm gonna extract out of this, and what I'm gonna extract out of a function instantiation info will be a tuple of the name and the parameters. So that is how we will compare things. And I need to do the same thing for equality. Multiple return values, no. A function only returns one thing. I don't have support for tuples in the language at this point yet. I will probably want to do that, but like in second phase, when we already have a full version of the compiler that actually works, we can compile stuff into images, we can run programs, then I think as another exercise, like, okay, we have a compiler that works, how do we extend the language? And tuples are a thing I want to add. And I also have support for arrays in the language, but I have not done any of the work on that yet. Which means I don't have strings either yet. For now, we have ints, characters, and booleans. But at some point, yes, I'm planning to have that. So here, basically, what I'm saying is comparing this thing for equality or for like order will be done only on the name and parameters. We don't do any of that on the definition that is cached as part of this. Okay. Well, I mean, that's exactly the point. The point is I will want to make string being an array of characters, but since I don't have support for arrays yet, I don't have support for strings yet. Because the big problem I have is my target language, Piètre, doesn't have a heap. So every single value will be... Oh, sorry. Here output is just the way I have named this particular import as opposed to input, which is those particular imports. As in, this phase of the compiler takes those types as input and those types as output. So here, the types that I use as arguments are which are the type parameters. So for a function foo that has like two type target arguments t and u because it's generic, this will be the types that are given to it. But those are output types in the sense of that they are the output of this phase, not input types as in the things we have from the previous phase. So they will be the type arguments. So if I call foo with instantiated with int and character, this list will be int and character. And yeah, the problem with arrays, which is where I don't have them yet, is again, I'm targeting Piètre, which is a language that doesn't have a heap, which means I cannot have an array just be a pointer to a segment of the heap or something like this. All arrays will have to be on the stack. And that means that I will need to have dynamically sized type and dynamically sized stack rollout and everything. And that's going to be a nightmare, which is why I haven't done it yet. I have plans for it. I know how to do it. It is like something I have considered, but it's going to be making a lot of things a lot more complicated. So I'm going to wait until I have a first version of the code generation before actually attempting arrays. I'm doing a lot better. Thank you so much. I've missed like a month of streaming, which really sucked, but doing better now. So, with this done, that means basically that we never attempt to do a function instantiation when we see its definition. When we see its definition, we only validate its type and we register it for instantiation later, basically. And then we do all of the instantiation at the end when all the types are known, meaning that we have the guarantee that we can do recursive function definitions with having to run into the problem of like attempting to define other functions. We will know all the types, so we can do all the type checking. So that means What does that mean exactly? That means that I will need, whenever I validate a function type, that means I put it in the cache of functions whose type I know, and I need to register it for instantiation, because if I do that, it means it wasn't part of the symbols yet. So I need to insert a function instantiation info thing into the instances. Instances is not a good name. Queued instances? Maybe better, yeah. So here, I insert the type into the known type, and I insert into queued instances. I will be inserting a function instantiation info that will contain the base name, the type parameters. Well, the problem is I could do something like this, allocating more and then like faking a heap, for instance. The problem is this would be very complicated because I don't have arbitrary indexing into the stack in Piètre. Piètre has only a few very small number of instructions, and the only thing I can do is roll the stack by a given number of things, which means I would need to basically, since I will have like a stack growing because I have recursive functions and so on, I would need to also keep track not only of like return values and everything, I would need to keep track of the stack depth to know how much to roll to like unpile the entire stack to go access the heap. It's not impossible. It's worse than having dynamic values on top of the stack, I think. Because like again, no like direct addressing. It is the same problem I run into when I do things in brainfuck, where like using as a stack easy, trying to simulate a heap monstrous. It's of course even worse in brainfuck. But yeah, again, like I would not. The problem would be I would not be able to have an address in the heap. I would only be able to have an address relative to the heap. So every time I try to do something that puts something from the heap on the stack, I would need to rotate all of my heap to put it on top of my entire actual stack to put the heap on top, then roll into it to get to the part of the heap that I need, then duplicate that, then rotate all of the heap again to put the heap back in place. While at every single point in the actual code, having on top of the stack a thing that keeps track of the heap depth. It's worse than having dynamic sized values on the stack, I think. But it is possible, just nightmarish. So here, actually, do I want to make the name? Do I want to make the function instantiation info take the name since I know the name? Yeah, I don't think I need to keep the base name. And since I'm already caching the definition anyway, let's make this a bit simpler. This is the name, which is base name plus type. Yeah, that's why I'm not doing it. And as a result, this becomes a lot easier. This becomes on name and on name. So to do equality of function instantiation info, we do actually, maybe this doesn't have to be, is name is hashable. My queued instances becomes a hash map from name to input function info resolved, to distinguish again from the output function info. And now this goes away. We wrote this for nothing. That's fine. And that means here, this becomes a very basic insert func name. And the definition will be, that's actually this function info that is put in our cache. Okay. So that's validating a function type. Perfect. So we can go back with this done, with all of these top level shenanigans done, we can go back to what we were doing last time, which was validating the expression in a constant. Again, we are mostly duplicating the thing we had pre-refactor and cleaning it. It's a lot cleaner now. The main thing I had last time that I did not finish was here is validate const path expression. We are validating an expression of a constant, which must be possible to evaluate at compile time, and we found a path. Path being a name that we have resolved in the previous phase. So rather than just having like an identifier, like this is x, whatever x is, we have, where is role defined? It will be defined in resolved. We have this thing, which tells us, hey, that name in this context is a built-in type, a built-in function, a struct, an enum, a constant, whatever it is. In the case of a constant, the only valid thing is another constant. Anything else is wrong. So if we have anything else, we report not a const, that's the end. And validating another const value, I don't think we actually... yeah, it's easier to make a function than trying to inline this. Validating a constant name will be checking that it has been given no type arguments, because functions constants don't have type arguments, so it should have 0 here. If that's not 0, it's wrong. But here is where we need to go recursively and to the other definition and do the cyclic definition checking. So this becomes given a name, and will this be a name or this will be a base name? I suppose that makes sense. There's no type arguments are separate. Yeah. Given this base name, we need to validate it. We need to make sure. Oh, and we need its type. So we need to do a validation and then get the type out, basically. I am tempted to change something. Here at the top level, I have made my validate things return always like never give me a type, basically. Like give me unit and always succeed, because it's fine for analyzing a definition for it to fail, basically. Because if A depends on B and B does not actually type check, or like has some kind of error in it, we can still try to continue analyzing A. It's fine. But here that means, oh, I need to analyze B because I depend on it recursively, but I then need to be able to proceed with analyzing A. So what that means is I think we need... No, we don't need to return the type. We can call validate recursively and then get the type from our state. And if it's missing, that means that type checking failed, but that's not an error. We can just... Can we? I was going to say, we can just continue type checking things, as in like, oh, this constant A calls something X. Can we continue doing type checking there? Or will it have, since it has failed, do we give up? And both options are possible. We could say, well, the type is unknown, and we use the type panic or something, void, something like this, which means all of the type checks succeed. Or we just say that this branch cannot be checked at this point, and therefore that A cannot be checked because it depends on something that cannot be checked. I think I prefer the latter. So I think what we need here is one of the many functions I had in my old context module that no longer exists. Well, no longer exists. Still exists, but is no longer the way we do things. I think I will need a retrieve type, which is going to be something that, given a base name, Well, given a name, I suppose. Yeah, I suppose given a name, and in some kind of monad M that will be more constrained later, will give me, in my validate monad, a type. That is what I need to be able to validate the thing. And retrieve type will have to do a few things. It will have to check in the dependencies, maybe that type comes from somewhere else. Then it will have to check in the local cache. And then if it's neither found in the dependencies or the local cache, it must be something that is local that we have not defined yet. For instance, again, another type alias, another thing. We need to do that validation and then check the cache again. So I'm going to just do that and put monad here so that I have the name of the things in the cache visible when I do that. So what we're going to do is that's probably a good way to do this. There is, and I've used it before. Give me one sec. I want to go back to the old context file. I have done a thing where I will have several monadic things that give me a maybe value, and I will basically want to return the first one. And I was using a sum. There we go. By applying call on something. Yeah. Because a sum, if I look at Google again, given some foldable alternative thing, gives me one of them by tracing the thing. Yeah, that's what I want. Okay. No. Well, the thing is, I don't want them to evaluate. What did I do here? Well, the thing is, okay, I need to look at alternative. Because would something... What are the instances of alternative? Because maybe obviously is. That probably means I will need to have a way... let's write it the boring way. We'll clean it afterwards. So retrieving a type is I do a view S on my VI dependencies. And what I do on it is a lookup of the name. That gives me a monadic maybe value. And it is going to be a value if indeed that name was found in the dependencies coming from other modules. What we're going to want to do is basically, if that is nothing, then we will want to try something else instead, which is why I was trying to look at the sum thing, but I don't think I can guarantee that my thing will be alternative. So I don't think I'm going to bother with that. Maybe with laziness? No, let's not bother. So we try this, and if it's nothing, then we try something else. Then we try looking up in the local definitions of the thing in the current module, which will be uses, because this is a state, no longer a reader, looking at the types that we have actually compiled, lookup of the name. If that is still nothing, there's probably a better way than doing those on nothings. Let's write the function that I want, and then let's check Google to see if it exists. Because what I want is basically some kind of folding function. I want to find first, I'm going to call it foo for now. It's going to be given some list of monadic maybe A. I want to return a monadic maybe A. Foo of an empty list returns nothing. Foo of a list that contains something and... No, I already have the type, which means I could already do a Hugel there. Because this is going to be basically do x, what's going to be x on nothing m foo xs. That's basically it. Let's have a look at Hugel and see if it finds something for this type. So I have a list of maybe A. Or I guess I could go even further and say this is an alternative f, and I have some m of f of A, and I want to return an m f of A. But I don't have a guarantee that m f of A is alternative. Okay. I don't find anything with that search. If I restrict to maybe, perhaps? First, just M in GHC, actually. Take computation returning maybes, tries each one in order. The first one to return a just wins. Yeah, that is... returns nothing. If all computation return nothing. That's what I want. But that is... kind of ugly to depend on... like to include GHC itself. I don't know. That feels inelegant, right? Maybe it's not. I don't know. Depending on something of the compiler itself, feels like it ties my code to the compiler in a way that I don't think I'm comfortable with. So maybe let's make that a function in our prelude. Can I put this away for a second? I have all of those on nothings thing. Let's try this, and let's call it again. So GHC calls it find first just M. Okay, I don't like this name at all. If I look at alternative again, because this is basically a sum, I guess it's a sum M in a sense. Yeah, I'm gonna name it like this for consistency. So we have some kind of... I could even make it an applicative. I don't even need monad here, I think. Oh, I guess I'm using with M. I have the monad constraint. Okay, let's make it monadic. So we have some kind of monad M, some kind of foldable F, some kind of alternative A, usually consonants for things, T, let's say. Oh, do we want foldable or traversable? Yeah, foldable. Okay. Actually, how is it implemented? I'm curious. If I go back to this was called first just M. Do they do it manually? They do it manually. Okay, so basically the thing we were doing. Well, no, they use the fold M. I'm wrong. Okay. Well, the downside is I guess this is not short circuiting, so we can do better. Maybe fold M is. I don't know. Okay, so we have some M, some foldable L, F, some alternative T. Our function takes as an argument a foldable thing. Oh, but if I generalize it to foldable, then of course I need to fully traverse. That's why they use fold M. Maybe I don't want the foldable. Maybe I want to hardcode this for list so that I can short circuit. So I have some maybe alternative thing, and I want that maybe alternative thing. But if I make it for any alternative and not just maybe, then I lose the ability to clearly, easily say, oh, short circuit on nothing or whatever it is. So maybe I can make it unfoldable then. So I have a foldable thing of monadic thing that give me some kind of alternative. And I will want to get some kind of monadic result in the end. This is gonna be indeed a fold M. That's correct. I'm saying that the GHC code is correct, thankfully. The B case is going to be the empty case. It's going to be the nothing case of alternative, which is empty. Okay. So it's going to be, I'm going to call this function go. This is going to be the empty case coming from alternative. And this is going to be, and then it's 0.3 basically. Okay. And go, what does go do? Is it just doing, given some, how did they implement it? They made it specifically on not on maybe. Okay. Yeah, it is just I have my current alternative thing. No, I don't. I have pure empty because I am in the monadic context. And go is a lift A2 of this. Applying this between. But do I lose a short circuiting there? Or will the value not be? No, I think this is fine. We can try this. So I think I might be able to just rewrite this way. Now let's try this by loading into GHCI since the project doesn't compile at the moment. Let's load just this file. But it's not gonna be. It's gonna be annoying. So maybe let's just actually just define it. Let's import control applicative import data foldable. And let's try, is that the correct syntax? It is. To define this. Couldn't match. Okay. So let me make this explicit again, just so that we can check the types, because something is wrong with the types here. So I'm going to say that there's a go function. That's not actually required, but just that the types match. The type of go given fold M needs to be, takes the B thing, whatever it is, an A thing, which is part of the foldable, and returns... Oh, but it doesn't need to be a fold M. It's just a fold. That's what the problem is. So this might be still correct. Okay. So if we try again, I open. Oops. This. I copy that. I close this. Okay, it's happy with this. So if I try this on, let's create a small, oops, sorry, I didn't see your... Yeah, I've never tried lean actually. I'm curious about it. How is it so far? Let's make a foo function that takes an int and returns something in IO by doing print of that int. I actually name, I could put n as being an int. And then if odd n, then just n, else nothing. Oh, yeah. What do you mean? Is it because I have made a mistake of being with no prelude? I don't know what you mean here. Oh yeah, definitely something is wrong about the prelude not being... Okay, so let's reset this. Except, of course, I need control applicative. I need import data foldable. Then I can try again. Okay, so now I should be able to go back to this idea. Okay. And of course, this needs to be a pure thing. It returns a something in IO. So the type of foo is function that takes an int and returns an IO maybe int. So if I do foo for foo 5, that's a list of monadic actions that return some kind of alternative, maybe something. So I should be able to do this, and if it is working as we expect, it should only print... Well, no, it should print both, actually. And return the 5. But if it returns the 5, because 5 is the first odd value, but if we have a foo7 here, it should not print the 7, it should short circuit. It prints a 7. So that's wrong. And that's because since I have generalized to alternative, I have to go through the action. I cannot short circuit. And since I cannot short circuit, I can't apply the alternative. I need to evaluate the action. And therefore, this fails. So we're not going to make it on any alternative. we are gonna make it on maybe A, so that we can short circuit and not execute the things that we don't want. And we are gonna make a go function at first, and go is gonna be so I have the first argument is the state I'm propagating. If it's just it's tricky actually. How did this actually GHC do it? Let's go back to have a look. They use a fold M. Oh, of course they do. Because I need the result, the monadic result of the previous thing to be given. Yeah, okay, that makes sense. So that becomes a fold M, which means the starting value is not in the monad. And go can be a case of we have a result, we forward just the result. So pure just the result, basically. If we have nothing, that means we need to evaluate the next thing. I'm gonna rewrite it explicitly. I have accumulator and action. And if my accumulator is nothing, I return the result of the action. If it's result, I forward the result. That, with this definition, should avoid basically the action. So if we go back and do that again, now we short circuit properly, because we use this to short circuit the action. We stop whenever the monadic action gives us the value we need. Okay, with this ASUM M in our arsenal, let's go back to here. And now I can do this as being a this thing, and there's 3 different monadic stuff I'm gonna do, and then I'm gonna be able to give them name and avoid those on nothings. Is gonna be lookup in dependencies, lookup in local types, attempt to validate. And this will give me a maybe value at the end in my current monad. And on nothing. And I guess I'm not even going to do an on nothing. It's going to be enough to use an ensure. Excuse me. Which is a function I don't have yet, but I have been assuming the existence of so far, which is we're going to be in some kind of monad that is able to accumulate warning and errors, and is able to try to resume evaluation, given a maybe value, continue only if that maybe a value exists, otherwise start short-circuiting and failing. And this is a tiny bit more readable, because now we have given names to all of those things, those different actions. And lookup in dependencies is going to be that. Lookup in local types is that. And attempt to validate is our last case where, okay, we didn't find it in the dependencies from other modules. We have not already resolved this thing. It needs to be validated first, which is how we will detect cycles. And that means we need to retrieve its definition and then we need to call validate basically on the base name, and we do have the base name, right? We have the full name even. Okay, that makes sense. So it's called name base. That's not great. And what we're going to need to do here is find the definition of that thing in our current scope, which will be, I'm going to do this thing I had before, where I have the monad here. This is going to be in the definitions we have access to, because that's the whole thing, is we need to have access to our list of definitions to be able to do things with them. So this will then be a views of the definitions, and we are going to do a lookup of the base name. However, this one, if it fails, is not an error we can recover from. This is not like this is not something. This is like, because here why we use this ensure thing is the only way this fails normally if everything went okay is we have attempted to validate something, but validating it failed. Because we didn't find it anywhere else, we tried to validate it, it failed, we cannot give a type because it failed, therefore we forward the error. But that's normal error, like this user error, perfectly fine. However, this not finding any definitions means we've already been through the resolve phase, but we have something that we know must have a type that somehow is not found. If we ever find this, then that means something went wrong. That's an internal compiler error. That one we can do on nothing m. Report ice. And there's going to be, let's see how we've used it. That's exactly what I'm doing. Yeah, I'm short circuiting so that oh, actually I need to fix something in the. Well, I think it's fine using empty is fine. I am short circuiting, which means basically the second. Oops, let me go back to where I was. Retrieve type. Basically, if one of those actions returns a value, I don't execute the others. That's the whole point of this asum thing I've been doing, which is basically if this gives me nothing, then we try this thing, and if this gives me nothing, then we try this thing. Or do you mean maybe maybes within maybes? But I'm not sure. Like we are already discarding the actions that we don't need. Like if this gives me a thing, those are not evaluated anyway, which was the thing we were trying to do. So this is gonna be. I forgot. How did we name things? Okay, so it's whatever kind of validation we are doing. We are trying to do type lookup, validation type lookup. That tells us the context. The actual error is definition not found. And the details we want to include for the bug report would be something like, that's just a string, and it's going to be the base name. Show base name. There we go. So that's not an actual like proper error that is strike and recoverable. That's a panic. We are reporting an error because we have something that should never happen if the assumptions about our program are correct. Now, with this, we get the definition. Which, again, at this point we always have, because if we don't have it, we panic. And now I can do a validate Yeah, I'm sorry. I've switched my settings to try to prevent those bots from showing up, but I don't want to prevent people who are not subscribed from chatting. And the second I allow people to chat, even if they're not subscribed, bots swarm the thing. It's very annoying. If you don't mind reporting it, that'll be very helpful. Reporting requires me typing an error message, and since I'm not typing on the same computer, I would like to switch keyboards to actually do it. So if you don't mind reporting them, that'd be lovely. Thank you. So with that done, we can call our validate top level function because we have the base name, we have the definition. This will do nothing basically. It's perfectly fine. I mean, nothing. It returns nothing. It's just a unit. It will update the cache accordingly. However, if this has been done, then our result should be in the local types. So I can just do a lookup in local types. That gives me the type in the end. If it failed, if I could not validate it, then that's fine. That means that if this lookup fails, the only reason why it fails, because we have already eliminated this case, is validating it here gave me an error and we never inserted it into the cache. This returns nothing, and the ensure here propagates the error to the caller. There we go. Retrieve type done. So now we can go back to what we were doing. We can unpack, we can go through back and through the stack and go back to the thing we were doing. We were going through path expression. And here I have found that this constant depends on another constant. That's perfectly fine. So I have the name, which is a base name. I will need to do a retrieve type of a name. Actually, gonna say base name here for readability. Of base name and no arguments. I'm almost tempted to make a pattern alias for this to avoid, because having empty list like this, yeah, I might do that. Where do I use built-in? There we go. Thank you so much. I'm gonna use a pattern concrete name that to a base name associates a name. And a concrete name is just a name with that base name and no type arguments. Wait. There's something wrong. I just realized. This is fine. I'm gonna go back to what I was doing. This is a concrete name made from the base name. Retrieve type, and that will give me the type. So that's gonna be constant type. And that will be wait, do I still okay, I have two errors I've realized I need to fix. So here, this will be here I will need to also retrieve the value. So that's not enough. So I'm going to use the same logic as retrieve type, but for something else, which is going to be for retrieve constant. So it's going to be constant. The result of this will be retrieve constant, I suppose. And will I need the concrete name? What is in my monad? Do I need to have them as name? They could probably be base name, since constants have no argument. Yeah. I think this name thing is wrong. Okay, let me just finish this. It's going to be retrieve constant base name. That's or even name at this point. That's fine. Which we will need to write using the same logic as retrieve type. Okay, there I have realized a name does not contain just types. It contains, for the type arguments, it contains names, which means here when I do the validate function type, I'm saying, oh, the name is the base name plus the type parameters. That's not true. Those are types, and I need names. I need to know their name. Do I? Can I change name to have just types? That's fine. Or do they need to be actual names proper every time? Can the argument to name be something else than other names? No, it needs to be names. I need to know exactly what I'm talking about. So this doesn't work. So I'll have to figure out given some type parameters, how do I construct a name from this? And maybe here what I will need is not... Maybe the answer is simply here, I don't need the type, I need their names. I need to know what those things are, and their types can always be retrieved from the name. The other way around doesn't work. So that is moving the problem down the line, but that now should work. Okay. And last, to finish this, we will need, I've made retrieve type, I will need to do a very similar logic for retrieve constant. That should give me a typed expression. This thing it should give me. So let's do the same logic. This should give me the retrieve constant. It should give me this thing. And that's going to be basically the same logic as this. Given some name, we're going to look up in dependencies, look up in local constants, and attempt to validate otherwise. I guess this is almost exactly the same thing. Except, aha. That means when I get things from other modules, I will need... I was gonna say, I will need... Like here I've added the dependencies that are coming from other things. Maybe I don't need to do that. It's going to be a tiny bit unclear, and this will need documentation, but since this state that I'm going to carry around for the process of my validation, I initialize it to whatever I want, as long as I can clearly separate what is my output of the process from the input of the process, and I think the output is basically the symbols. That's what I need out of this phase. There is no reason for the types, constants, that are coming from other modules to not be the initial value of my state. I will add to those, but that's fine. I want to add to those. So maybe rather than having these dependencies kind of thing, I will just look into whatever my state is carrying, which needs to be initialized with what I already know from my dependencies, basically. I already know about those types. I already know about those constants. Yeah, that feels reasonable. And of course, for functions, I will, yes, that's going to be the type that I need to care about. Yeah, okay. So I think this is what we're going to have to change, and I will have to document this. This will be initialized with things that I already know, and I will just add to them so that the output, the state at the end of my validation, will be what I already knew plus what this module knows. And symbols will be, and that's going to be the same for symbols, I suppose. So this is going to be the incremental change. So that means I can remove the previous thing, which is good. And that means retrieve type doesn't have to do lookup in dependencies. This function that we've spent some time making is no longer required because this is ensure of lookup in local types and on nothing m attempt to validate. Although that being said, no, on nothing m will not be correct. So I think I'm going to keep the asum m. But dependencies no longer exist. This is lookup in local types. So lookup type, and otherwise attempt to validate. There we go. And for a constant, it's going to be lookup constant or attempt to validate. This is going to be looking at the constants and attempting to validate what we do if we can't find it. For a constant, this will always be a base name. It's going to be looking up the definition. Actually, I should keep it called base name to make it clear that it's not an actual name. Although I have not been consistent with this. Okay, we try to look it up in the constants that we already know about. Otherwise, it means since we know that it is a constant, we know it is in scope, it must be a local one. We retrieve the definition from the reader that we have access to. Not finding it is an internal compiler error. We must have a definition for this thing since we know it exists. We try to validate it, and we look it up again. And if this lookup fails, it means validation fail, and we will report the error accordingly. Perfect, and this is a lookup type there. Okay. So now this gives us a const expression, a typed const expression, which is what is stored in our constant thing here, which means at long last that a const path expression, if we find a path in the constant, some foo name thing, identifier, it must be a constant. It cannot be anything else. If it's anything else, it's not a constant, it's wrong. And the way we validate it is we check that it doesn't have any type parameter because it's not allowed to have any. And we retrieve the typed expression. This will do a lookup in the definitions of other modules. If it's not found in the definition of other modules or in things we have already validated, it will do a lookup in the definitions of this module, attempt to validate it by pushing it on the stack, which will fail if there is a cyclic dependency between my constants. If there isn't, and validating that dependency constant succeeded, it gives me the typed expression. And this is now the result of this function, and that's the result of this entire thing. We are done with validate const path expression, which is what we have done everything this evening so far for. Okay, so in validating a constant expression, we have done const path, that's done. We have done validating a cast last time. Field access. Have we done validate const field access expression? I don't think we have. Oh, we have. Validate const field access expression. Okay. So what we do is we look at the value of the type of the validated sub expression, which we must know at compile time since it's a constant, and we know must be a struct. If it's not a struct, the error field access not a struct. If it is, however, we look at the name of the field. If the field is not found, fail does no longer exist. Report now. If we cannot find the field, then the name is wrong, we report that, and otherwise, we report the field value. We find the field value. Okay, so that's correct indeed. Next, what have we not done? Call expression, that's report not fatal, but that's an error because function calls are not allowed in constants. Array expressions unimplemented, I don't have arrays yet. Index expression unimplemented, I don't have arrays yet. Validate struct expression, however, this is going to be where we're going to have some interesting things to deal with. I think everything else is done. I might not have the names for all of those yet. For validate negation expression, validate addition expression, and so on. So I'm going to need a bunch of small functions. I've chosen this path of having a bunch of small ones rather than inlining everything in the big case switch here. I think it's better. So, but first, I think validate struct expression is going to be very complicated because we're going to need to port all of the type resolving logic from the pre-refactor version. So a struct expression, we do have the struct name. That's convenient as input. And that's coming from resolved. That's from common. Struct expression, that is a path info. Okay, it's a path info resolved. So it's still pointing to like, oh, it's pointing to this name with those type arguments. Okay. So, validate struct expression. Let's go. This is going to be a function that, given some monad m, and again, we will want to have more constraints at some later point, and given a path info resolved, that is, again, a name, a path, a.b, c, whatever, that we know must be a struct name, and given some fields, which will be, are they already resolved at this point? No, I don't think they are. Because I have not called in my call function here. Yep, I'm giving the function, actually, interestingly. Okay, this is the function to call recursively to validate the sub-expressions. I'm not going to do that. I'm not going to do instead validate struct const expression. Because it's going to I think it's going to be different enough from what we have to do in the case of a function that we would probably want to have distinct cases for both, and maybe we'll factor in a separate function what they have as overlap. So that's, and the fields will therefore be, what will the fields be? Whatever is in here, they are going to be that. A non-empty list of tuple of identifier and with a location, an expression that has already been resolved. Okay? Probably want to deduplicate. That's gonna be another thing to do later. At the moment, I'm using type families for resolved and stuff. Like there is this AST representation thing that decides are we passed, are we resolved, what types do we use. I will probably will I want to make the output the validated expression type, which is distinct from the others? Will I want to make it as part of the trees that grow type family approach, which means suddenly I can reuse a lot of the for info, else info, and so on that comes from the previous things? Because a lot of this is duplicated and doesn't need to be duplicated. Probably. But again, it's easier to duplicate for now and deduplicate later. Back to validation. Okay, so we have that. What do we do with all of this? Validate m, and what do we return here? We are in the context of a const. This is going to be a typed const expression there again. Okay, so here we have a path info resolved. We are going to need to do a validate type kind of thing that gives us a type given the path info that checks that it is indeed a type and gives us a struct. We don't have validate struct yet. We will let us have at some point. So, okay, we get the validated type. Try validate type of the struct name. Now we have to do a case validate. Well, I guess first we will want to do validated fields is gonna be some kind of fold M. I might want to make so for each of the fields, so I have a field name and a field value. We will want to do validate const expression of the field value. Oh, does validate const expression take a thing with location? Yes, it does. Perfect. So we do that. We do a try so that we can do all of the fields. We can try analyzing all of the fields so that if one of them is wrong, we don't short circuit. We still collect errors from all of them. And so that gives us maybe const exp. And we return a tuple of field name and maybe const exp, which means this is in fact a traverse. Which means the function we apply on all of those is traverse with try validated const expression. So now that gives us a, in our validation monad, list of tuple identifier and typed, maybe typed const expression. And I can ensure that, but I'm going to need to do a series of sequences there, I think. So I'm going to want to sequence the tuple into a tuple that contains a maybe value into a maybe tuple. Like sequence can be made into, if I have a tuple of 3 and just foo, this will be just 3 foo, so that we can sequence once. I wonder if I can I do the thing where I do, rather than doing a sequence and then a sequence and then a sequence, can I actually compose the things? I think I've done that in another place. I think for the validation, for the resolving resolution, get compose, yeah. I think that's the right approach. Let's do that. So this is a traverse 2 of compose try validate content expression of the fields. Then I get compose that. And that gives me, I'm gonna copy those names because I don't want to ensure them just yet. I have done this before. How did I call the non-ensured ones yet? The ones that contain a try attempted. Let's be consistent with my naming. Attempted. And now this is ensure attempted type. Ensure attempted fields. So we have collected errors from everything. And now at this point, we know we have the values. If any of them failed, we have thrown the error to the color. And now we have the types. Now we have the fields. Great. We can have a look at the type. Probably gonna need the name is the thing. Probably gonna need the name and the type. Spell of this. So I will need the name to use as a key for a bunch of things. So, okay, I have found the type of something. Like this thing was indeed a type. I will need to return its name and its type. Okay. There we go. And the others that don't exist yet will have to do the same thing. Okay. So now we have the type, and we can look at the type. I guess here I can already do type name type info. I can deconstruct the result of this. And here I can do a case of the type info. And I am only interested in one case. Or is type. I am only interested in the struct type. Oh, I do have the name as part of the type. I do have the name as part of the type. Okay. That's good. That means I don't need to return the name. This all goes away. So this is back to being validated type. And here, therefore, I have a struct type that has the struct name. And it has the list, which is basically the only thing I need from the struct info. It has the list of fields and the type. Wait, should that be? It should be a type here. Struct fields. And we're going to do something here. Any other type. Maybe actually I'll make a validate struct thing that does this kind of validation of I have a type name, give me the struct info, basically. Yeah, I think I'll do that. So this will be instead validate struct, and the validate type will be instead. So I'm gonna do it validated fields here. This will be ensure of this, and here I will have I will have the struct name and the struct fields as a result of doing an ensure on the attempted type. There we go. So this case thing will become part of validate struct. It's going to be exactly the same thing as this. But instead, will be giving me the name and the fields, which, as we have said, is a non-empty list of tuple identifier type. And validate struct will be given some path info. It's going to be validate type. This must be a type. If it's not a type, then it's already wrong. And I guess I can write it 0.3. Then is then forwarded into this function that in the case of a struct type with a struct name and fields, fields, just name fields is enough, will return pure of name and fields. And in any other case, will report an error, not a struct, or something like this. I don't exactly remember my diagnostic codes. Do I have a not a struct? I have error, not a struct. Perfect. And that's the role that needs, therefore, to be in that's the path name. Okay, so I'm gonna have to have path info here that is decomposed into those things, and I give it as an argument to validate type. I then bind that into this case, and the error not a struct takes the path name as an argument. There we go. That means those here are not gonna be. Actually, I probably don't need to validate anything at this point. I probably just need to return a type based on the information I have at my disposal. So let's put this as unimplemented for now. Unimplemented for now. I'm gonna have to change this, I think. I'm gonna stop the alignment here, that's not required. Okay. So I can change this here to say that this is validate struct rather than validate type. And now, by the time I'm here, I have the struct name and the struct fields. What do we do in the old code when we encounter a nice const? There we go. When we encounter a struct expression, we do resolve the struct type, but we do the parameter mapping here. That's an important bit. Okay. That is something that we're going to need to rewrite, not from scratch, but everything we've done so far is going to be different. So like it's going to be none of the code that is here that exists for this can be ported. So we're going to have to rewrite that logic. Ah, yes, of course. And that's where this is going to be very much of a problem, because we might not be able to get a type. Because a struct name because type is always concrete. All of the type arguments are known. However, in the case of a struct, struct expression specifically, not all type arguments need be provided. We can infer the types from the expression. So, in the case of a struct, based on the base name, even if we have the path arguments as part of this, we cannot necessarily return a type. Maybe that means that validate struct and validate type needs to be separate. Validate type must mean this is a concrete type. I need to be able to validate it. It must be concrete. While validate struct must be slightly different and return something that keeps the ambiguity of the fact that we might not have the concrete type yet. It must return the base name here, probably. It must return what we had here, which is the struct info and the which is the fields basically, and the parameter mapping. Okay. Let me think about this for a second. Let me think about this for a second. I think we have the same problem. The fields cannot be a type because the fields could be unknown. We don't know that. We don't know what the fields are supposed to be. Because the struct that we are pointing to could be a generic struct. So I think for the fields, the only thing we can return is a non-empty list of identifiers. Those are the fields that are expected in this. Ah, no, we need more than that because we need to do the mapping. Okay, since I need to take a break on this because I can't figure out exactly how to solve this evening, I mean, I could spend some time and try to figure it out. I might just do something else instead, and I'm gonna answer your question. I am compiling a fake language that is meant to be a subset of Rust. Lot simpler than Rust. Doesn't have traits, doesn't have like dynamic memory allocation, nothing like that. But it looks like Rust. There's one thing at the moment where, given the choice of parser, I have a slightly different syntax, and therefore the Rust formatter doesn't work currently. But otherwise, except for that one thing, Rust formatter, Rust syntax highlighting should work on our made-up language. It looks like this roughly for now. As you can see, we have structures with like type parameters. We have functions with like type parameters and so on. The reason why we have such a small subset of Rust is that our target is not a classic like compile to assembly, make a binary kind of thing. We are compiling to an esoteric language. And specifically, we are targeting Piètre, which is an esoteric language in which a source code is an image. And I have here an example of the first program that the backend of our compiler has generated, which is this image. This is a valid Piètre program. It does nothing very interesting. It points only 2 characters. Malbolge is impossible to generate. Piètre is much easier in comparison. And it prints 2 characters and returns. It does almost nothing. But that is what we're targeting. And it has a very limited instruction set. It doesn't have any heap. It doesn't have any like a random memory access. It's a stack that you can roll, and that's about it. Which is why we have so many restrictions on the language. But even if the target of our compiler is silly, no one is using Piètre seriously in production. I am treating this project as basically as seriously as I can. So the compiler is written as close to a real compiler as possible. I'm using Alex and Happy for the lexer and parser, which are the ones used in GHC for the actual Haskell compiler. Although I'm probably going to change Happy into megaparsec at some point, but that's another story. I'm trying to be as close to a real compiler and as explicit in the code for it to serve as like kind of an introduction to compilers in a sense. That's the project. And currently, I am refactoring the analysis phase. So we have like the parsing phase that takes the source code and gives me an AST with like a bunch of tokens in them. Then I have the name resolving phase where like, okay, this function calls something foo. What is foo? Is that a constant? Is that another function? Is that a variable? Is that an argument to the function? Is it a type parameter? What is foo in this context? And now we are doing the second half of the analysis phase, which is, okay, we have resolved SSA as the intermediary. So we have resolved all of the name. Now we're doing the type checking and validation. Those two used to be one phase, and I have split them. That is the refactor I'm doing. Then we do a lowering into IR using an SSA form that is meant to be compatible with the LLVM-IR. A side project I want to do at some point is to do an export from our IR, our SSA form into LLVM-IR to be able to actually compile it to an actual image, just like to try to make some binaries out of the thing for fun. And then we will have code generation, which is a phase I don't have yet, that will generate bytecode kind of, which is like series of Piètre instructions, annotated with more things. Linking, because we're going to have a bunch of functions, we need to figure out their addresses, and then generating an image. And the linking, generating the image, we already have, the backend is done. So when we're done with this gigantic refactor of the entirety of the analysis phase, then we can move on to the code generation phase. And in a few streams, few being a number between 5 and 30, I suppose, we will be able to start generating images from Rust-like source code. But yeah, that's the project. And here, so in this validation, I have this problem of what I was doing already in the pre-refactor version. I don't know if I have an example here. Yes, I have an example right here. No, I don't have anything. Since I don't have any heap in Pete, the things I can do with like dynamic types are very limited. So the linked list requires like types that can be like pointers or anything. This, no, we're not gonna do anything like this just yet. Maybe as an extension to the language when it works, but yeah, but like the meta type system is too limited for that at the moment. Again, once we have a first version of the language that kind of works, we can try to do extensions. I want to add tuples in the second version, but anything more complicated, like pointers for now, we don't really have. We have fake references at the function argument level, and that's about it. So here the thing I'm trying to fix right now. We allow this syntax. Here S is a struct that has a type argument, and here I'm saying the type of Y is S with whatever the argument here is, that we can infer from the fact that this S is constructed with the field being a X, which is of this type T here. So we can deduce that the type here, the argument to S, is the same T that is the argument to the function itself. That works in the old code, and now I have to figure out how I want to make that in the new code. And that is the thing where I might... that is exactly correct. The at in there, oops, is where this different, like this is where the Rust formatter isn't happy. Rust would just say that, but that is slightly ambiguous in the grammar, and happy is not happy with that, I suppose. So for now, I've done this as a change so that I can use my parser. I'm gonna at some point change from happy to megaparsec, mainly because I want to get rid of this. It cannot distinguish between this is a path expression that is followed by a block, or this is a struct expression that contains fields, basically. This would not be valid as a thing to have like a name followed by a block, but in terms of how the grammar is expressed, I don't have the look ahead enough to be able to disambiguate. So it doesn't know if it needs to shift or reduce there. Shift to continue, like to continue, reduce, like, okay, no, this is actually a thing that is self-contained. That's a path, and those tokens need to be treated separately. So to solve that ambiguity, I've added a character. But again, I will at some point rewrite the yeah, it doesn't make any sense. I agree, but in terms of like purely shift reduce, it doesn't know if it should shift or reduce purely based on the information of like what we have passed here, basically. So having the at makes this explicit. Yeah, so the thing I'm trying to do is figure out how I re-implement this logic of I need to figure out, I can't, like here, this validate type can't give me, it is a path. It is a path, but it is, as far as my AST is concerned, there is a difference. Maybe this could be actually a solution. Come to think of it, this could be a solution. I have a different kind of expression in the output in my AST between a path expression, which is something that points to a path, a local variable, a function argument, so a constant, whatever, and a struct expression that contains the path to the name of the struct. Where you're right is that I could remove the at and make the left-hand side of the struct expression just be any expression. The problem with this is that I cannot, in the case of a context and a struct expression, I cannot just resolve the left-hand side as being any expression. I will need to make sure it's actually a path expression. It's doable, though. And that would avoid a rewrite with megaparsec. I'll think about it. That's a good point. I mean, maybe I can do something better there. I guess I could just like, when I do the validation there, I have an expression on the left-hand side. I was like, well, it must be a path expression. If it's not, it's wrong. Huh. I'll think about it. Maybe that's a way of keeping happy for now and not having this at in the syntax. Maybe that's the right solution. Yeah, again, I'll think about it. The Lexer is Alex, which is the one that GHC uses. Just gives me a iterable list of tokens basically. The only thing is Happy and Alex are like work together. So Happy basically calls the Lexer to get the next token whenever it needs a token basically. So whenever it does a shift, I need a next token. Calls Alexa to continue passing the input stream where we are. So I don't generate the full list of tokens and then run a parser on the list of tokens. The parser is aware of the Lexa and is able to like give me next token basically. But yeah, I'll think about it. This would allow me to keep Happy, which would be nice. By just making a small change to the AST and a small change to the validation function we don't have yet. So yeah, probably a good idea. So here again, the problem I have is I want to. I have a name of a struct, but I might not be able to know its type yet. Not from the name, because maybe the type arguments are not provided and are either not provided or placeholders. How do I want to do this? How did I do it before? I go to context, which is one of my old pre-refactor file. Struct. Resolve struct type. And I have then check struct type. There we go. I found a struct definition. Perfect. I force the definition. It must be resolved. That's not a problem in this case. I look at the expected type parameters, and for each of them... Yeah, Haskell can be very readable if you are familiar with functional code. It's very easy to make Haskell unreadable, and one of my challenges for this project is I want to try to make everything as readable as possible. I am not always succeeding, far from it, but some of this is like, I am not naming this like R. This is a resolved info. I'm trying to name things, basically, where Haskellers love their single letter variables. So here the validation that I do is, okay, the number of type arguments to the struct must match the number of expected arguments or be 0, I suppose. It's kind of basic, but you know, a lot of Haskellers fail at this very first step. So here I written the definition. And I guess, what do I need from the definition when I resolve a struct? I only need the fields. I mean, I am guilty of M for monad, but when I have something like monad M, here in this context, this is very clear that this M thing is a monad. Plus, there is also a difference, which is that is a very common name for it, which means if you have an M in a type, 90% of Haskell code will use this for a monad specifically. For variables, however, is where I'm a bit more strict. As a side note, a convention I love, the one letter that people use for comonad, the inverse of a monad, is W. And I love that. I think it's great. Okay, so I think what we need to do is the same thing here. When I validate a struct, I will need to return whatever is required as... I can't return the type, that's impossible. But I can return the base name, that makes sense. I can return whatever part of the definition is required. And what is required as part of the definition will be... Where is struct info? Where are you? It will just be the struct values. Hello, how are you? Yeah, it's going well. It's slow progress, but steady progress. It was an unplanned stream, but my Monday was unexpectedly free, so I decided to make some progress on the project. So here, do I return the entire definition? I probably don't need to return the entire definition. I probably just need to return the field information. But do I need to leave this as an unresolved path info? Or can I? I guess no. The fields will have to be types because they will have. They will. But I might not be able to know their types just yet. I will have a concrete type for the expression associated with them, but I might not be able to have a type yet. Oh, this is tricky. Okay. Maybe I don't do it this evening, so that way I have time to think about what I want to return here. There's gonna be definitely some non-empty thing for the fields, a hash map from identifier to something for the type mapping. But in all, what I know for sure is I cannot call validate type, and I will need to document this. Validate type is incorrect here, because I cannot create a concrete type at this point, which means this will need to be something similar to this, kinda. Except I will not be validating the type of the path parameters, and the only thing I will care about here is struct. It must be pointing to a struct or maybe a type alias. If it hasn't been resolved by that point, maybe substitution will need to be performed. I am not sure. I am going to leave it at this for next time. And anything else will be not a struct. Okay, and I'll think about it for next stream, which will be tomorrow evening, if everything goes well. Okay, so I am putting that problem for later, I think, which means whatever the result of attempted type will be, we don't know yet, and whatever ends up being here at the end is something that I cannot do. But at the end of this, I will have a validated type. I must, if this succeeds, if this function succeeds, I will have the type of the expression at the end, which for now is unimplemented. And if all goes well, the result will be a typed expression, the type of which will be the validated struct type, and the expression will be an output struct expression, which looks like this, where I will need the name, the struct info. Oh, I will need the struct info. Interesting. So I will need to construct a struct info, which in this case is slightly different. It's just I have there again decided to decide later what those things would be. Although I think at this point I know. At this point, this will be typed. Therefore, this will be a non-empty list of identifier. Do I even need the struct info as part of the... Yeah, I am implementing some very, very basic type inference, not as complicated as going all the way to HM. Something extremely basic of like types are like expressions are unambiguous, which means things can use placeholder types and let the type inference work for them. It's extremely basic. Like it's just in the old code, it's just of like, okay, this struct needs like I know its type arguments, and I know the type of the fields. I can do a mapping from like a from what I have seen in the expressions. The type must match from this. Like here's the matches that I have. Can I find a value for all of the type arguments? Are they all like do they all agree? Yes, I have found the type arguments. That's basically all I do. And for function arguments, I do the same thing, where, okay, I know the type arguments to the function. If they were not explicitly provided, let's look at the arguments provided to the function, and let's check that this gives me a concrete type for every type argument. That's basically all I do. That's not very since again my type system is very limited. I don't do anything more complicated than that. But I am not sure exactly how to do this representation at this point, which is why at the moment I am not doing anything more complicated. Function archetype, this is going to be a type. This is absolutely not a name. Okay. Do I need the struct info as part of the that's too complicated for now. No, I will not be able to do something like this. And at the moment, like to do would need to like yeah no I'm not be able to do anything that complicated. The only type inference I have is for again struct expressions, constructing a struct without giving the type arguments, and function calls. That's about it. And for like local variables, but I need to be able to know their type from the expression. If I can't determine the type from the expression, then that's an error. I don't do anything more complicated than this. This might be something I might look into as an extension to the language when a first version exists. But again, for now, I'm focusing on making the first version exist and then documenting it. I don't know if I actually need. Do I need the struct info as part of this? Because the type expressions are type. The type will contain everything about the struct that I will need moving forward. I might not need the struct info here. I don't think that's required. Because the type information will always be alongside the expression. And the type information will be everything I need moving forward. Yeah, I think the struct info here is just not required. So to create the struct expression at the end, I will need the actual name of the full name, qualified name. Well, no, it might mean that struct info might just not need to exist at this stage of the compiler. Which, removing things is even better. So I think at this point, the only thing I need is the actual unique name of the struct that points to its own like symbol name, kinda. And even that might not even be required. Even that might not even be required at this stage. It might be there because no, it's not even there as well. The typed expression on the left, the type must be a struct. Oh, that being said, here, I suppose adding stuff like the name and the struct info, the upside is I don't have to check the typed information surrounding this expression. I don't have to check the type of the expression on the left-hand side to check that it is indeed a struct when I have already validated it, to then extract the information that I need. So maybe I need the struct info here to avoid having to do lookups that might fail and the result in internal compiler errors in the next stage of the compiler, which is the lowering to AR. So maybe I do need that, and maybe the struct info. Yeah, it's probably going to be very different. It's probably gonna contain the name, and I don't think I need the identifiers. I can decide later, but I don't think this needs to be, because at that point it will be concrete. So the name of the parameters is useless, because it must be concrete in the resolved expression, which means that is just a struct name and fields, which is, yeah, identifier and type, which is basically the information of the struct type, which means that's a struct info. Or I guess struct type. Let's be consistent. That's a struct type. And that way, that's basically caching for later. I know that the type of this is a proper struct, and here is the struct type. I know that this type expression is a proper struct, here's the struct type, which means I don't have in future phases to, I could even here remove the typed expression, because I don't need the type. I know it is a struct. I have already checked it. The type here adds no information anymore. Okay. For const expressions, this is going to be the same. Struct type and non-empty identifier typed const expression. Okay. So that is, I think, correct. That's the correct target. We're not there yet. So we will need, at the end of this, we will have struct type, and the result of this expression, which is typed, will be a typed thing where the type is struct type of the validated struct type, and the actual expression within this typed wrapper will be a struct expression, the first argument of which will be the validated struct type, and the second argument of which will be the fields. That is the success path. And now fields equals validated fields unimplemented as well. Okay. So now that gives us roughly the shape of what we need. I guess validated fields already exist. I've already done that. That is this traverse to of the fields. We validate that it is, each of them is correctly a const expression. We apply a try so that we will try to compile all of the fields, even if the first of them fails. We try to recover and do the other ones. We compose to put the maybe there. We traverse to bring the maybe all the way back to the top. And we ensure so that basically we fail again if any of them has failed, but we did try all of them. So now we have the fields. The only thing that's missing is now to get here the proper struct type, we will need to do the type inference. So this validate struct might not, it's not the correct term, I think. I think it's going to be a retrieve struct. I guess no, it is a validation. It is also validating that this thing is a struct, but it will also just give us some information about it so that we can do the field type inference there. The way I do it in the old code, yeah, I have this, still I have the path at this point. And my mapping is either, interesting. So I suppose resolve type, okay. And now placeholder path. Resolve type is this one. Okay, for a struct, I have checked. Okay, I could relax this requirement. The requirement at the moment is like, okay, there are type arguments expected of this struct. Well, if they are, either none of them is given or all of them are given, but maybe allowing placeholder as in underscore. Maybe I could relax that and say, well, you're expecting 3 of them, you've given 2, I'm assuming that the others are placeholder. I can probably relax that, yeah. That doesn't feel wrong. That being said, that could be a pretty easy error of like, oh, the number has changed and suddenly it assumes placeholder. At the same time, if it assumes placeholder and it cannot figure out the type from, it might be fine to do so. I might do that. Okay. So basically, I return the type information, which is a path info resolved, so it hasn't been validated yet fully. It could still be, yeah, okay. And then the hash map of, for each identifier, either the type that was provided or placeholder. So for struct, this will definitely be hashmap identifier to maybe type. Was a type provided? Or do we have a placeholder instead that we need to figure out? And here is what I don't know what to return for the fields, because the fields will not have, I will not know their types, is the thing. What I kind of want is a partial type, a type that may contain some nothings somewhere. I want a type that may have holes, basically. That's what I want. So that I can then look at the actual concrete type of the field, which is a foo of bar of int, and compare with the type with hole on the left hand side, which is a foo of bar of underscore, and then do a mapping of like, oh, this underscore is an int. But that also means oh, that's tricky. I'll need to know that the thing left on the placeholder is, I'll need to know the name of it to be able to figure out. Okay, I'll think about it off stream. That is something that was complicated to do in the old version of the code. That is something I'm struggling to do in this version of the code. This function doesn't work yet. Unimplemented. This function doesn't work yet because it's missing basically what does validate struct give me, how do I then validate the fields. But its output here will be valid when this is done. which means as far as this function is concerned, we are done-ish with validating a struct const expression, as in we are in a constant and we have encountered a struct expression. Did we check that it was valid? Okay. Which I think is everything we can do at this point for constant expressions to get back to where we were pre-refactor. Except, no, that's not true. We need to do all of those small functions, all of the validate thing, because I have chosen to make one of those for each of them. That's going to be verbose as hell. Oh well, that's fine. Except a lot of those are actually... Yeah, assignments don't exist in constants. Just gonna do a replace of expression with const expression. I could probably do something a tiny bit smarter. This is every instance of validate of a bunch of letters that are not space followed by exp, and I want to replace. And it needs to be a not. It needs to be not D at first because I don't want validated. There we go. And I want to replace. Let's try that again. And I want to replace that with, so again, not D here. And I want that to be a word binary, I think. There we go. That's correct. And I replace that with validate this const expression. There we go. So this one is correct. I don't need to change it. This one I've already changed. Validate addition expression becomes validate addition const expression. And there we go. Okay. Now I just need to introduce a function for each of those. Just. Let's put them after struct. Let's put them here. I will break this file into several files. But since I'm in the middle of the refactor for now, again, it's make it work first and clean it second. Okay. A lot of those will be extremely similar, but let's do them one by one. This will be a function that takes, given some monad m that will actually be more complex than that later, it will need to be like a monad diagnostics and maybe a monad validate or something like this, we will see. This will take a typed const expression and return in our validate transformer, which I will rename to validate T to be consistent with transformer naming conventions, a typed const expression. I will really want to try to see if I can make this, like, I have a separate type for const expressions and for regular expressions to be able to restrict const expressions to something, to a few things that are only valid, like to only valid things. The problem with this is that it ends up duplicating the const version and the non-const version of those validation functions. I could try to go back to a trees that grow approach again. and make it so that const expression is actually a subset of expression where some of the fields are labeled as void and therefore cannot exist. But that is verbose. And I have to think about it to see how monstrous it is to have duplicated version of all of those. Or maybe I use some type class magic to be like, can I extract the const value of this, basically? So what do we do here? I suppose that the first thing we need to do is, unless the type info is exactly Boolean type, then the Boolean negation is wrong. We're trying to do a Boolean negation on something that's not a Boolean. Except we shouldn't be using equal equal. We should be using type matches because we want to accept void, basically, not of a function that returns void. The panic type should be accepted. So the type must match Boolean type. And if that's not the case, then report. And do I have a diagnostic for this? I guess it's just a wrong type, which I think is no longer going to be those. It's going to be type and type here. I'm expecting one of those, and I got this one. So it's going to be an error, wrong type. I'm expecting Boolean type. I got type info. Okay. Now, the const expression, since I have checked the type, this is a tiny bit annoying. What have I done for like the cast? I could not check the type. I could just check the expression. Because the problem is like, if I've checked the type, like, oh, the type of the expression must be Boolean. The problem is like, if now I try to do a case of the typed value, and I don't get a Boolean literal, then something went very wrong. That being said, I probably want to have that kind of sanity check just to be able to find errors in the compiler. So here, either I have a bool literal const expression, because I am in the context of a constant, it must be known at compile time. That's perfect. Our result is a typed with a Boolean type of a value that happens to be not B. If I have literally anything else, despite the fact that I have just thrown an error if I don't have something that is a Boolean, it means I have something that was tagged as Boolean, but that was not a Boolean expression. Oh, it could be a panic. It could be a panic. I can't have panics in my constants because I don't allow function calls in my constants. So here I can even remove the type matches altogether. There is no possibility of panics. I guess unless I detect like, oh, you've done a 1 divided by 0, therefore the result is panic, this will never actually be executed, therefore all type checks beyond that succeed. But no, 1 divided by 0 should have type int, and therefore we should be able to still type check it. So no, I don't think panics are possible in the context of a constant. And it doesn't hurt to have type matches as a safety guard, but I think here there is no case where another kind of constant expression must be allowed. I've tried to say not on a thing that was supposed to be a boolean and I didn't get that. That's an error. That is just an internal compiler error. Const expression const boolean negation expression validation. The error is not a literal boolean value. And the details I want to include for this crash report is value and show of the typed value. So in this case, big crash report because we checked that the type was Boolean, but the value wasn't a Boolean. The known compile time value wasn't a Boolean. Okay. We can just copy and paste this for validate int negation const expression, where it must match int type. Otherwise, I'm expecting int type and I got whatever this is. And if I find an int literal const expression that's perfect, I can return minus that integer at compile time. Otherwise, I am trying to find an int and I did not get one. There we go. Addition is complicated. I'm gonna do all but addition for now, because addition is slightly overloaded. I will allow plus on things that are not integers. I will allow plus on strings at some point and arrays. So those are gonna be the int ones. So those functions are all gonna be, and I might decide to not type them at the top level because they're gonna be an expression of both of those arguments need to be int. If either of them is not an int, thank you for tuning in. And my usual stream days are Tuesdays and Thursdays, and some weeks I do some extra days, and some weeks I don't do the normal days because I can't always do that, but the normal is Tuesday, Thursdays. And yeah, good night. Thank you for tuning in. Because all of those 5 things will be, the left-hand side must be an int, the right-hand side must be an int, and the result will be extracting an int literal from both of the things, and then applying something on them. So this is gonna be validate binary int expression with the function to apply being subtract. And in fact, for reason that will become clear in a minute, this will be pure of subtract. Validate multiplication const expression will be validate binary int const expression with pure of multiply. Validate exponentiation will be a validate binary int thing with pure, and whichever one is the proper operator for ints, which I think is this one. And the reason why we use pure and we put the result as being monadic is because this will be safe div mod, which I think is how I had implemented it pre-refactor. Let's go back to core. Safe div. Yeah, there we go. Oh, I have safe exp as well. Interesting. Oh, because of course negative exponents makes no sense in this context. Okay. So instead here, I will want to use safe exp. Okay. Now save div mod. Will take int and int and return an analysis. Instead of having safe div that takes either div or mod, I'm just going to make something that returns both. Like this. Import error divided by 0, known at compile time. Otherwise, return x div mod y. And yeah, suppose... let's put it, since I will want to have some constraint on the monad m, let's put it with like the arguments one per line, like this, monad m, int validate m int. There we go. Okay. So now the last thing we have to do is to define validate binary int const expression. And I might actually define those as being part. Yeah, there we go. Part of the definition of how to parse a const expression. And in this, maybe then I will want to, it's fine. That's fine. Maybe I will want to like change this validate binary expression with that takes, I think it's fine. Okay, so validate binary int const expression is the one we have to do now. Already there. It takes two typed const expression. And it takes, before that, a function that two integers will associate an action in the validate monad that returns an int. We will be in some monad m that will have more constraints later. And the result will, of course, be validate m, and this will be a typed const expression. Given a left-hand side and a right-hand side, we will try... They're already typed, so I guess... So unless type info of the left-hand side type matches int type, report error wrong type. I was expecting an int, and I got whatever the type info of the LHS is, which I suppose I could, I've done this a few times, I could introduce a local helper expect type given some monad M that will actually be a monad diagnostic at some point, given a type that we expect when we expect a specific one, and given a type that we found, returns validate M nothing. And this will be given some expected and some actual types when, unless expected type matches actual, report error wrong type, expected actual. There we go. Now there's a few places where we do that, so we can replace them. For instance, we can say expect int type of the type info and replace that. We can replace that with it's expect type, not expect on its own. Expect type Boolean type of the type info. And I'm sure there's a few more reports. Let's check back for error wrong type. Here's one, for instance. Expect type validated type type info resolved expression up. And I think that's all for now. Okay. So here we do an expect type int type of the left hand side, expect type int type of the right hand side, and if we are still there, it means both of them matched, which means we can do I will probably want to do the same thing here. I could go one step further, I think. With those expect functions that I think I will move to their own file at some point, I can do an expect int that given a typed const, oh, maybe expect const int, typed const expression will give me an int. And given some typed stuff, I will do expect type int type of the type info, and then for the value, I will do this. If it's an int literal const expression, perfect, I will return the actual int. Otherwise, const expression validation, not a literal int value. I can do the same thing for Boolean, which returns a Boolean. This expects to be a Boolean type. This expects to be a Boolean literal. This should be a Boolean. Perfect. Which means I can go back to validate int negation const expression, get the value by doing expect const int of the sub-expression, and the result will be a typed int type that happens to be minus the value. And for a Boolean, this is going to be the same thing. But with const Boolean and Boolean type. Now, to validate a binary int count expression, I can do the same thing. Expect const int of the left-hand side and the right-hand side. Check that the type is int. Give me the int value. And I'm going to call them x and y. Which for a binary integer operation, I don't feel too bad using single letters. And the result of this will be to apply whatever this function f that was given as an argument to x and y, which means I can probably rewrite it as being a lift a2 of f on expect const int of the left-hand side and expect const int of the right-hand side. Now it's a one-liner. There we go. And this one is wrong. This is not the value. I could make this one into a one-liner, but I think it's more clear like this. Okay. What is missing? We're missing those. Those. Addition is complicated. I'm going to write it separately. Because here I'm going to have to check that the type checking is going to be a bit different. Do I have string type, despite the fact that strings are not supported yet? If I look at my type, do I have string type? I don't. Okay. Because here, addition will be valid on more things than just int. So here I will have to do a expect type one of, which will take a list of types and check that actual matches at least one of them. Unless any of the types in expected type matches actual. Expected here is a list. So this will be here for an addition where I have two sub-expressions, the left-hand side and the right-hand side. I will need the type of the left-hand side to be expect type one of. Maybe it will be more complicated than this, because if I end up supporting on arrays that can be any type, it will not be that simple. So maybe I will need to write an ad hoc expect here. For now, I'm just gonna write it as this. It's basically the same thing, but to signal that, like, okay, this is different. And then I expect type of the right-hand side to be the type of the left-hand side. So the left-hand side must be one of the valid types, and the right-hand side must be the same type. And now I can do a case of the type info of the left-hand side. And if it is int type, then I can do an expect int, just expect const int, just to simplify, which will be doing some redundant checks, but maybe, oh, in that case, I don't need to do, oh, I guess I can do that way then. I don't do this check, and I just do a case type info of the left-hand side, and I just deal with the things that are valid. So if it is an int type, then I can expect a const int of the left-hand side, and I can therefore do a lift a to the int value will be a lift a2 plus of expect constant on the left hand side, expect constant on the right hand side, and we return pure of a typed expression which has an int type and the value of which is this int value, which I could make a one-liner, but I would rather keep it as a two-liner just for clarity. And if it is any other type that we support, like an array or a string, whenever we have those, then we can add those cases here. And otherwise, we can do a report error wrong type with a list that for now is just int type. And maybe this will need to not be types because I will need to be able to. Maybe this will be another case for partial types, because I will maybe want to be able to say, oh, this is int or array of something, whatever it is inside. So maybe this will be another case for partial types that we don't have yet. For now, this will be that with the type info of the left-hand side. Okay. That's the addition const expression. There we go. What do we have left? Oh, I seem to have erased the comment with the missing. Oh, here they are. Just gonna move it up. Here now we have all of the values on which this is complicated. This is where I had some complicated code pre-refactor. Let's go back to core and let's have a look. There we go. This is what I had. I had this thing that, given two values that can be compared, gives me a maybe Boolean. A function that to two typed expression gives me an expression resolved. Interesting. Which is, I think, how to construct the result based on the... Oh, but this may be for function, isn't it? Yes, it is. I want the thing for constants, which is a bit simpler. There we go. Compare expressions. That one is kind of tricky. Because here, basically, we have to go for structs, we have to go recursively. Okay, so let's do that. I'm gonna use this thing. I'm gonna use it as a template, like I've done validate binary int const expression. Basically, I'm gonna do a similar template for validate binary const compare const expression, which will take why was the maybe? Why is the up function returning a maybe? What sense does it make for maybe to be? Oh, is it like, why is the maybe? Oh, because I want to deal with equality, I think. No. What is compare expect? How did I do that again? Ah, okay, that's the case. Okay, this is basically return nothing when it's equal and return something otherwise. That feels unnecessarily complicated. That feels unnecessarily complicated. So maybe we won't do that. Maybe it's enough to have just a boolean, and we'll change that if it ends up being wrong. Our two arguments will be two typed const expressions. And this will be a validate m, and that should give me a boolean. Well, no, I guess it can give me directly a typed const expression. That's const. Okay. I have some function f, I have a left-hand side, and I have a right-hand side. Okay. First, expect type. The type they expect is the type of the left-hand side, and the type I'm checking against is the type of the right-hand side. I cannot compare things that are not of the same type. Then when that's done, I can do a case of the typed value of the left-hand side and the typed value of the right-hand side. And I just have to deal with every possible case. Okay, that feels correct for the base case. We will want to have struct const expression, struct const expression. What do those contain? They contain the struct type and the fields. Perfect. And here that's a bunch of const expression. Except I don't have strings at the moment. And for all of those, it's just pure of applying the function. I suspect, this might not be, it might not be that easy. No, it is. There is no problem with the extraction. I've done the extraction by doing this. So it is all gravy. I don't have to have, those functions cannot fail in any meaningful way. However, here is the complicated case. I probably don't need to do this struct info thing because I have the struct type. Oh, that's a bit ugly. Although I suppose since instead of here I'm doing is like for each name of a field, I'm comparing the fields basically by doing pairwise, like find the name of that field in the list of expressions. Oh no, I have to do that because I have no guarantee that they will be given in the correct order. So no, I think I have to do that. So the struct type, as we have this decided earlier, is name and fields. Okay. So for struct fields, is that, oh wait, is that the correct thing? Yeah, I suppose. For struct field of the struct type, which I'm almost tempted to just struct type, decompose right there and then. So for each struct field, maybe I want to sort them. No, I don't want to sort them. Because at runtime, if field X is initialized before field Y and X results in a runtime error before, like, it needs to throw before field Y is executed. I can't reorder them, so I have to do this. So this remains the same. Fatal no longer exists, it's called report now. I mean, report doesn't exist yet, but that's the name I seem to have decided on. And now this needs to be, aha. I guess I can just go back to validate binary compare const expression with the same function f. On the left-hand side field and the right-hand side field. I'm going recursively. And I do a sum of comparison. That makes sense, I think. Well, no longer no, because I was using the maybe thing for equality, but since I'm now doing just anything, this is purely an AND comparison. Okay. That's the same thing as before, but a tiny bit easier. Are there any types that are valid at compile time that we don't handle? Const expression could be an array. We don't handle those. Struct we handle. Bool, int. Oh, no, I do have string literal const expression. Fascinating. I thought I didn't. Well, I should handle those here. Okay. What am I missing here? Now, with this, I am going to need to define all of those in terms of that new function we have just created. Oops. This is all going to be validate binary compare const expression. Oops. And now I need to decide, okay, given two values, what is true, basically? Which is what I was doing before with this complicated thing of that's the wrong one. I don't currently use Haskell for work thing. I'm looking for a new job, and Haskell jobs are not that common. But when I was using Haskell professionally, I was using this exact same setup. Uh, I've tried I've tried a few years ago. It might have changed nowadays, but I tried the how's it called again? The server, the compiler, like backend language server thing for Haskell, and it was a tiny bit slow. It was great to have like a jump to definition and everything in Emacs, but it was a tiny bit slow, and I basically don't use a lot more than just syntax highlighting and compile line stuff just for my yeah, just it was slow at the time. It's probably a lot better nowadays. But at the time, sometimes I would have like freezes on autocomplete on typing, and I really don't like my Emacs freezing when typing, so I disabled some of this. But there was like stuff like autocomplete and jump to definition and so on. I need at some point to give it a try again, just because I think having those things work would be fantastic. Um, uh, my last job I lost due to health issues, which is kind of sucks. I'm looking for a new one now because my health has improved significantly enough that I can look for a job again. But I had to basically take 2 years of sabbatical because I couldn't no longer work. It sucked, but you know. Yeah, things are mostly. I'm at the point where again I'm looking for a job now, which is a sign that things have definitely improved. I think I changed a thing, which is rather than being rather than being a function that takes two values that are ORed and does a thing, I think instead it's going to be a function from ordering to Boolean. So equality, the function is it is equal. I mean, I'm a bit slow about the job search because I have other things I want to do in the meantime. I'm not too worried personally because I've been working professionally for 15 years at this point, and I have a number of big companies on my resume, so I'm not worried at all personally. I am more worried in general in the state of the job market in tech. uh, the US economy is in pretty bad shape. A lot of tech companies are like cutting jobs at the moment, claiming it's because of AI. I don't actually believe that. I think it's more because of like the state of the economy. And there's also the fact that like all the big tech companies are doing nothing but AI, and I don't want to touch it with a 10-foot pole. So there's been a bit of that. But otherwise, the job market sucks as it is, but my situation is a relatively privileged one. So when I actually spend time looking for a job rather than doing this, I don't expect it to take too long, but I could be wrong. I hope I'm not. So here I will want to do f of compare. There we go. So if two things are equal, it means that to compare that gives me less than equal or compare tells me equal. Difference means it's anything. Oh, I know where I was doing the maybe thing. It's not that simple. Because of structs. Because of structs. That's the problem. Because on a struct, if all of the fields are equal, like a field being equal doesn't mean that the structs are not different. So I need to handle the maybe case. That's why I was doing the maybe thing. Okay, I understand now. So let's go back to for all A ord A takes two A's and returns a boolean. And here I do and returns maybe a boolean. And let's do the same thing I was doing, which means where is comparison expression again? Compare expressions, there we go. So here, so this gives me a maybe boolean. Interesting, okay. Oh, and I have a wrapper that takes comparison expression, okay. With the default case, that's why, okay. That makes sense. Okay, okay, okay. So I will need this function. I will need to know the default case, which is going to be a boolean. This will return a typed const expression. That is correct. However, I am going to make this thing a go function, recursive here within the thing. That will take, and I'm going to go LHS and left hand side or right hand side, and this go. I might actually do this. I don't need the types at this point. And this go will take a left value, R value, and it will be a case of those two things. And here, when I go recursively, I use this go thing on. Since I have already validated the types, I don't need to check. So this is the typed value and the typed value. I'm basically reinventing the previous version. I I don't know. I'm very lucky to, at my age, have no back or neck issues. I'm lucky. I used to have a better setup where this laptop was plugged into this screen using a dock on the side. The problem I have is I would then be running OBS and everything on the laptop itself. And it can get pretty toasty in this room, especially when I was streaming in the summer. And when my laptop, which is doesn't have like a graphic card or anything, it is purely a work laptop, starts thermal throttling, OBS drops to like a frame per second, and everything collapses. So what I'm doing is I've given up on this setup. That with the winter approaching, maybe the temperatures will drop enough that I can go back to it. And I'm working on the laptop with a capture card, and the capture card is plugged into my actual gaming computer, and I'm streaming from my gaming computer by putting the camera on top of the stream coming from the capture card. So that's exactly what I'm doing. I'm capturing the screen output of the laptop. Yep. You know, it's a extremely complex setup for no reason, but for no reason, for a good reason, but it works. Because yeah, again, running OBS on this poor old laptop, the gaming PC is Windows. It's my last Windows machine. And it's still on Windows 10, despite Windows 10 having expired. I have not upgraded to 11. I don't want to upgrade to 11. When I move away from Windows 10, I will install Bazite, one of the Linux gaming distributions, because Linux gaming has become good enough that at this point I don't want to keep. The only reason I have a Windows machine is purely for games. And now that Linux for games has become good enough, I see no reason to move to 11. all of my other machines are some flavor of Unix. This laptop is a Linux using Manjaro. My small server running there is running FreeBSD. Most of like everything else is Linux or Unix. Yeah, the thing is like the running the end of life for Windows 10, which was supposed to be the no, I don't want to upgrade to 11. I really don't want to. It's a nightmare. Let me just actually think about what I'm doing right now. It's typed value here. I really like the XFCE. It's I've been using it for at this point probably close to 20 years. It's lightweight. It's great. Plus, the way I do things tend to be a lot of virtual desktops, one per thing I'm doing. Like I'm currently on the virtual desktop too, and a bunch of full screen windows in whatever I am, or maybe tiling, but rarely so. It's just usually just full screen, and XMC is perfect for that. Plus, it's so fast. That's great. Okay, so the compare goes away. Compare is no longer a thing. I use this F function. I am basically reinventing. Yes, they're linked to your monitors. I don't really mind because you can pin some windows to be on all virtual workspaces anyway. So usually my second screen when I work would be like Slack or something, and just like that is pinned to all workspaces. But otherwise, yes, that's true. So this gives me a maybe value is the thing. Yeah, you can pin. You can say like this. You can say like this window is always on the visible workspace. Oh, it shows up right below the camera. Perfect. So you can say like always on the workspace. So I would just like do that for the windows I need. So Go is not monadic, I think, because there are no error. No, they are. If the fields, well, those should not be errors. I have already validated the left-hand side. So if I have already validated the left-hand side, those make no sense as errors. They are internal compiler errors. Because I have a typed const expression that I know is a struct. I know that the fields there have been validated, and therefore that there is a field for each value of the struct. This makes no sense. This is not a field access field not found. That is wrong. That is a report ICE. This is const comparison expression validation. I could replace this string with just like using the call stack and getting the top value of the call stack, I guess. The error is field not found in struct. And the additional information I will want to add will be the struct type information by doing a show on struct type. And I will want to add as well the list of fields to see what is so struct fields to help with diagnostics, and this will be the LHS fields. And I guess it could be useful to also know which one, I'll see which one is missing with the difference. So that becomes also the case here. That is an internal compiler error. If those left-hand side and right-hand side are valid, which we have already validated by this point, a field must be found. A field not being found is an internal compiler error. Of course, here this would be the right-hand side field. Okay. Okay, so this gives me a maybe value. So at the end, I have here the maybe value. This will be pure of a typed expression, the type of which will be a Boolean type, and the value of which will be from, excuse me, okay, from maybe of the default case of going recursively. And so here is going to be the default case. Okay. And here, as a result, I need to re-express those functions, like equality const expression, as being what, how do I compare things? Here, however, I could simplify the thing I had before, I think. Nah, this is ugly, but I think this is actually the best solution. So I'm back to just basically doing what I was doing before, which in a sense is nice. It means that what I had arrived was in fact pretty decent. I am gonna put this in here. In here, actually. Compare expect will be something that okay. I'm actually move safe div. No safe div and safe mode will need to be used for other things. Okay. And with this, I now just need the I can just copy what I had before. Which is that. Oh, Boolean and Boolean OR. Have I done with those two? I don't know. Okay. Back to validation. Oh, Boolean and Boolean OR are included here by mistake. That explains. Okay. So, when I compare things for equality, if they're anything but equal, that's always a false. And if I don't have a conclusive answer after comparing fields pairwise in a struct, so if they're all equal, the answer is true. When I'm saying they must be different, anything other than equal is true. And if all of the fields of a struct are equal and we haven't decided yet, then the answer is false. Greater than must be for and inclusive equality false. Yeah, okay. I think that's correct. I'm gonna move them where they're used, which is here. And I suppose I'm gonna need two last ones, which I am gonna just move immediately because I know exactly how they're gonna be implemented. I will need, and I'm gonna move them up here, validate Boolean and Boolean or const expression. And those are gonna be, I'm gonna align with those, they're gonna be binary Boolean const expression with and or. There we go. And this will be the same thing as validate a binary int const expression. But instead, this will be something that gives me from two booleans a boolean. It gives me two types, and expect const boolean, expect const boolean. Oh, in case of int, oh, I do have a pure. Yeah, of course. Wait. That's not completely true, actually. I need to change a few things. Because here, this will give me an int, and that's not correct. I will need to typed int type the result. There we go. Here I will need typed boolean type the result. Wait, no, that's not correct. This is wrong. This is correct. This is wrong. Because f returns something invalidate, so I cannot just lift like this. I need to join, because otherwise I'll get a validate within a validate. So I need to join here if I want to do this way. I guess I can just do a join.f here. Well, no. The f it's in the, yeah, doesn't work. This is here, dot join. Okay. This is, of course, a binary Boolean const expression. That's the whole point. And do I have expect const Boolean? I do, with an error here, but that's fine, it's easily fixed. This can go away. Okay. And now with this, except for the struct type thing that we haven't done, I think we are done with constants. Okay, so the big thing that we have been stuck on this evening, that I will think about before tomorrow for the regular stream of tomorrow evening, is in the context of, actually, let me check quickly. Yeah. The thing that we don't have that we need to fix is the case of a struct expression in a constant. Which I think will just require a partial type that we don't have yet. Because I will just need to be able to say, well, the thing on the left-hand side, I don't know what that is. And I will be very tempted to make type a Barbie type that uses some kind of not there's another name than Barbie type, a higher candidate type that takes as an argument a functor to wrap the values. And in the case of type, the functor is identity, and in the case of partial type, it is maybe. And maybe I'll salvage something I've done in another project to use a type family to make it so that it actually maps to the actual value for identity to make it easier. Yeah, maybe I'll do something like that. And if I do that, if I have a partial type, if I figure out it's the right answer, what can we do with it? Oh, that's a lot of empty space. Yeah, it's for struct. It's gonna be for, where are you, struct? There we go, it's here. What does it mean to validate a struct? How do I check the type? I will need to have I will need to resolve the types of the field to partial types, I suppose. Because for every type argument, I will have a maybe type. So I will need to do type substitution on the definition of the struct to get for each field a maybe type like a type with holes, basically. So that gives gonna give me this will give me here this will give me for the field something that will be a partial type or something like this. And this, yeah, this is what I'm gonna have. And maybe I'll introduce a record to avoid having this complicated thing. But this is what I'll have. After I resolve a struct, I validate a struct, and I don't have the field values, importantly. I only have the name and whatever type arguments were provided. I will need to know, okay, look at all of the arguments that have been provided. If they are present, great, I can try to resolve them as partial types because they may contain placeholders. Otherwise, as an actual, as a partial type that may or may not be there. Then for each field, I need to do a substitution of, okay, given the type information I have that might be incomplete, this is what the partial type is. And return for each field this partial type information. And so this is what has been given, which might be incomplete. This is the translated type information of the partial type of the fields. Okay. And then what I will have to do with it will be where's the struct? There we go, here. Then I will have to look at each. Oh, it's going to be even more complicated than the partial type. It will be something where rather than partial, yeah, I'll definitely want to do some kind of Barbie type kind of thing. It will be either a type or a type name. Like, oh, here's a placeholder that maps to whatever the name there is. That way, I can then, for each field, look at this partial type and compare against the actual type of the field that was the value that was provided, and create, as I was doing before, a mapping from template type in this context to the corresponding type. And then I can check that for every single type I do have values, and that for every single type they all match. Okay, I think I have a plan of attack. I have a plan of attack. I think one thing is that I will probably not need this. I will probably not need this. I will need to know the list of the types, but maybe just a list of identifier will be enough. Because then if this partial type kind of thing contains the mapping, I can do the mapping for all of them, and then for each of those, I can go check. Yeah, I think that's enough. Okay. Okay. And that means that in the result validated, here I will need to change type. What I think I will want to do is, again, basically change it to be this, where it's gonna be type and with some prefix or suffix, type tree, I think, with f as an argument, and that f argument will be given to struct type and function type. And struct type of f will be here a type tree of f, basically. And function type of f will use this f type tree of f. Wait, here I'm never using it to wrap anything. That's not correct. It needs to be which means it's actually it's f of a tree, a type node of f, where a type node of f is that. There we go. And which means, yeah, every time I have type tree, there we go, type tree, type tree. And function archetype also takes an f argument. And this is a type tree of f. And this f will be very explicitly a functor, something that to a type associates another type, basically. Okay, and this means that type will be a type tree of what's the name? What's the name of the monad that does nothing? Identity. And partial type might be something like maybe. And type not partial type, but hollow type would be a type tree in which the functor is an either of an identifier. So we either have a type name, a template type name, or we have an actual type at every level. Something like this, where type tree is given this functor, which all three of them are, is this functor applied on the type node that is parameterized by the thing f. There we go. Yeah, I think that's the correct thing. Oh, I have function info here. Yeah, that's going to be something different, I think. I might want to change this. And I will probably want to see if I can reuse statements and things from previous, maybe by changing the expression type. Maybe I want to change the expression type and reuse the trees that grow thing. I'll think about it for tomorrow as well. Because maybe if and info and so on can just be the same compared to like common if info. Oops. Yeah, it's just expression body else. That's just the same thing. Yeah, the only thing that changes here is the expression. I will probably want to reuse trees that grow for that and deduplicate some of this. Okay. Now the thing is, I will need the utilities for the HKD stuff, HKT stuff, which I had poorly named HKD in the previous project. So I want to do that now. It's late. I kind of want to have a quick look at how I had done it before. Which project I had done that for? Was it for Hint? I think it was. Internal. That was a table name for this, but it was well commented. I'm gonna take this and move it to this project. Yeah, I'm gonna copy this file with a proper name this time into internal as higher kindred type. There we go. So the trick of this is this, basically. I have this HKT type family that to some given functor and a value, if the functor is identity, just associates the value type, and otherwise, if it's any other functor, maybe either of string, whatever, associates the functor applied to that type. Which means that if I use this for the type here, if I use this, in the case of type, since the functor is identity, this will be translated to type node of f. The f will be removed. And so at every layer, I will just have a type directly. I will have a type node of identity at every level. Which means I will never have to unwrap the identity anymore. And I have some unsafe coerce here, which is kind of horrible. Anyway, yeah, I'm gonna keep this. That's fun. And I will need it here. No. HK team. This will require some comments at some point. And yeah, we'll definitely want to use trees that grows to deduplicate all of that if info for maybe unless it's different enough. Name type, yeah, okay. Here I have better information. I have a range expression, but I could just make it. I could just like start making a list of differences. It would allow me to what I'm saying is basically I have this statement type parameterized by a phase of the compiler, passed, resolved, and so on. And I have a duplicated version for the validated phase because some of the internal types are different. And what I'm saying is I'm already doing some type families to say, well, when I am is it done? Not here, of course. When I am resolved, then the name type happens to be role, which is a terrible. Like all this is bad, but I'm gonna fix it. I could make more things in AST representation and start deduplicating things that can be deduplicated, such as reusing the same statement that I have for passed and resolved for the output for validated, just pointing to a different expression type, basically. Yeah, I will want to do that. I will probably do that next time. So now I have type, partial type, and holotype. I don't know if I will need all three. Yeah, I think that's fine. And that means that what I want, if I go back to result to validation, here I think I will need this holotype kind of thing. I think that will be enough. What I can do then is I can already prepare by copying it from core, although it's gonna change. I had a type diff function. Not called type diff. Maybe was it in context? Nope. Build type parameter map. That's what it was. Which is basically what I want to do. This will be given a holotype. I'm gonna call it partial type since I don't think I will need both the partial and the holo. Just gonna call it partial type. Wait, I might need. No, I might need. Yeah, that's annoying. No, I will need both of them. So I will keep this as holotype. Given a holotype that may not contain a type but might instead contain a type parameter identifier at any point, and a type I don't think I need to be in the validation. Nah, I might actually. No, I need because they could be wrong. Like I could have a template being like, oh, this must be an array of underscore, and on the right hand side I have a int, and that is not compatible. Therefore, I will need to. Um, I will need to. I will need to signal error. Okay, so yes, this will be given some monad m, returning something in our validate monad, and it will return a list from identifier to type. This is the type, the list of, for each missing type on the left hand side, here is the type I have found on the right hand side. Go on type 1, type 2, and if doesn't give me anything, then report an error. I expecting type 1, I got type 2. That's not gonna work because this expects a type. So that's already broken. Great. Do I want to emit an error per mismatch, or do I want to just fail on the very first? I think I want to fail on the very first one. I think. Because what's going to happen is, can I make more specific errors? I think it's no. I think I have a very simple solution to this, which is that I introduce a new diagnostic, which is not wrong type, but incompatible type, where the left-hand side is a holotype. There we go. Easy peasy. That will be the pattern. Pattern is a keyword. The reference, expected actual. There we go. And now I can go expected actual. Perfect. And now this is a this is where I have to look at, do I have let's look at the expected one. Do I have a left and a identifier here? That means that, okay, I know that this thing on the left-hand side happens to be the template type parameter t or whatever. So that means that I can return a list that contains the tuple identifier and the actual type that maps to it. If I instead have some information, then I can do a case of the right hand side, the actual type I got. Hello. I know it's late, I'm still at it. And here, this is all completely wrong because this is using the old type that no longer makes sense and exists. No, you didn't say anything, but I knew what you were thinking. Here, the annoying thing is I'm gonna have to, yeah, I'm gonna have to do this thing of matching both of them and writing a case for each of them using the type node thing. Up, up, up. It's gonna be the name. Name one. And what is the thing? No, I think I don't care. No, I care about the name. Okay. I'm just gonna do a thing. I'm gonna replace this by so I have an opening parenthesis, a bunch of things terminated by a comma. This is gonna be this, 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 and go, basically. Actually, it's gonna be empty list in most cases. Okay. So if I did not find, actually, I could simplify this by removing by doing this, matching the left identifier and anything on the right hand side, and then matching right. Here, only for a few of them, I will need to keep up the parentheses. There we go. So left identifier, right anything. Perfect. That's one mapping that we need to keep. If I have right in type and in type, it's perfect. Like it matches. I don't have anything to report. Likewise for Boolean type and so on, they match. I have nothing to report. For two enum names, to enums, I don't have anything to return, but I need to check. This needs to be just. I need to check that they do actually match, so that the name are matching. Which is basically something in the lines of if name one equals and name two, then empty list else, then just empty list else nothing. And I'm sure there's a better way to do this. But that's good enough. And for two structs, that is a go recursively on the two struct types. Well, they have to match though is the thing. No. Let's not go recursively, that's a bit different. Okay. So for those, I'm gonna have to do something a bit more complicated. Okay. And for function types, it's gonna be a bit the same. I'll need to do some sanity check to make sure that... Actually, since if any of them fail, it is just an error, I could probably avoid this on nothing. Just do that. That's pure here. And here I basically do the validation. I could introduce abort equals that. And now I can do when name 1 different from name 2. Well, unless they are the same. Abort. And let's have a quick look again at the types. And here this is pure of an empty list. The types match, there is nothing to get out of two enums. I'm just gonna do an abort here, and there's gonna be the basic case, which is gonna be an abort as well. Okay. Okay, those are the basic cases. And those are the complicated cases. So if I have two struct types, okay, I will want to do, since it's the type, the fields will be in the same order. I don't have to do any lookups here. So I can do, unless struct name of struct type 1 equals struct name of struct type 2. We don't do structural typing, but nominal typing. Abort. Then this will be a zip with go of the struct fields of the struct type 1, except it's going to be the second element of all of those, and the second element of the struct fields of struct type 2. So I take the type of the field of the first one and the second one, which on the left-hand side is it's the hollow type. On the right-hand side, it is the concrete type. I take the actual types, so I get hollow and concrete, and I do a zip with go, which is our function that gets the thing. So the result, is there a zip with m? Is that a thing that exists? Zip with m. It does in control monad. Perfect. So zip with m, the result will be in my monad a list of the result of applying this function together, which is itself a list. So the result will be a concat of this. And finally, for two function types, can this ever happen? No, it cannot. It cannot ever happen. I don't have, at least at the moment, I don't have syntax for function types in the language, which means a type argument can never be given as a function type. There's no way for this to be expressed. The only kind of function types will emerge as the use of a function as a value in a context. So this can just be removed. Okay, and now we have. Oh, check params. Do I need to do that here? I do, actually. No, I don't. I don't. The type parameters have already all been in line. That's the whole point of type. I don't need this anymore. Okay, perfect. Okay. Am I at the point where I can start doing this validate struct kind of thing? So I have a struct with a base name. I will need the definition of that struct, and I will need but the problem. Huh. I guess this would be. Yeah, I'm gonna need to construct a list of maybe types or whatever I've called them, partial types, to then be able to construct my list of holotype by doing something a bit similar to what I've been doing here, I think. So I create a struct with an argument that is not given. Its type is partial type. It's missing. It's nothing. And then that means for every place in the type substitution, yeah, I think that's what it is. I will need to. Oh, it's more complicated than I thought. Okay, since it's more complicated than I thought, I'm gonna stop here for this evening, and I'll be back tomorrow to continue with this. Thank you for tuning in. That was fun, and I'll see you tomorrow.